Okay, good evening. We start the evening session by a plenary by Ioannis Agathakos titled Deus Ex Machina, Emerging Opportunities and Perils in an Agentic World. You can start.
Well, hello everyone. So it's a great pleasure to be here today and present my thoughts and some preliminary results that I also have regarding this rapid and unprecedented evolution that we witness in our world with what is called agentic AI, because the word agents in the past was used to refer in different methodologies. But now we are seeing this idea of AI agents that are posed to and hyped by many that will transform and change our world in unforeseen ways. I couldn't help but add this slide today since we are in Athens, my special home city, and discuss about what exactly Deus Ex Machina actually means. Well, the term itself was coined by Marcus Vitruvius Pollio around the first century before Christ, but originates initially from the three great classics, Sophocles, Euripides, and Aeschylus, around 500 BC. The idea was, as you can see, this is an exhibit from the Museum of Thessaloniki, a reconstruction. It's sort of like a mechanical apparatus where a divine figure comes out of the sky to give a solution to a problem that was thought to have no solutions. And this is apparently solving an impossible problem, giving a surprising solution to the theatric plot. An interesting thing about Deus Ex Machina, which it means God from the machine, or apomechaniz theos in Greek, is that there is no actual evidence of mechanical creation, as it was created mostly of wood, but we have evidence in vases, for example. This particular vase, also around the 500 BC, discusses the divine transfer of Saturn, the son of Zeus, well, one of the sons of Zeus. He was quite prolific in this department, after he died in Tria, using the apomechaniz theos or Deus Ex Machina solution. So after this sort of description about where this title comes from, let me begin my discussion. So how do we go from the parallel of this divine entity that solves the problems in an unforeseen and unexpected way to these two images? Well, we will see that many people today, and I think there are some in an audience here that maybe know more about this than me, about the power of agentic systems. We see that they appear in literature today and in the news as omnipotent systems, able to solve basically anything. That could be the benevolent usage of AI. But I believe, and I hope I will convince you by the end of this talk, that they can also be used in malevolent ways and actually be quite dangerous. So my talk will be organized to introduce you some ideas that are generic. Then I will introduce some solutions that are the opportunities, the emerging opportunities, the good thing, the benign God from the machine. And I will end my discussion with the potential perils and some concerns that I have regarding the future. A few things about me. After I started my career, I'm going to start from my career only in the United States, as I was quite a few years here in Greece. I spent 4 years at SRI International, a research group that is credited with the creation of mouse and Syria, among other things, where I was a cybersecurity expert for the Department of Homeland Security and other agencies. I spent 2 years in Northeastern University, where I studied ways to harden software using compiler tools. And before I started my wonderful career at Montclair State University, I was in Amazon Web Services, where I did data provenance, and in the end, using static analysis tools, for what is called automated reasoning, a way to enhance agents. Jumping right into it, in the interest of time, this is an image that I find quite interesting to begin why this is an important problem. And I mean, we all know because we hear it every day, but it's interesting to see these three lines. So Google Scholar related publications over the course of the past 7 years. We see around in 2017, it's a very important time because this is when a very important publication in the area that many argue gave them the whole throttle for the development of agentic system. It was the technology of transformers. It was the very important seminal paper, Transformer is all you need, cited about 20,000 times to this day. Starting from this important publication, we can see in 2017, we have around 400 publications already. It was quite well received. 50 only mentioned LLMs, around less than 10 LLM and LLM agents. You can see that almost every year or so, we see a factor of 10 in increase. Reaching today, in the last year, we have about 160,000 total publications regarding transformers, LLMs, and LLM agents. Another point of importance, Hugging Face is a hub where somebody can download the agentic AI models. Observe that just one model, Llama 3.1, was downloaded just the last month, almost 11 million times, just for 1 month. And there are dozens, if not hundreds, of these models. So this is evidence of the overwhelming increase that the scientific community and the engineering community are using these products, right? Jumping from the academic world to the enterprise world, this is a study from Gartner, alongside with some anecdotal evidence that I picked up along the way, about, I'm pretty sure that everybody in the audience has seen that by using their applications. Out of nowhere, you see applications that were used in the phone to this format. Everybody now has a small agentic system popping up. You can see Zoom, transcribe live, on your browsers, they're asking you to do things. And then no matter what tool you use, you will start seeing, if you haven't already, agentic AI systems sort of like popping up without you expecting it. The slide on the left side of the slide there shows evidence of that based on a Gartner report showing that in 2024, in the beginning of it, less than 1% of enterprise applications had an agentic system in it. And we see that up to 2026, we expect up to 40% of worldwide applications to have a form of agentic AI in them, built in. Some AI funding trends. This is Crunchbase. In 2021, we see about $100 billion, almost 1/7 to 1/8 of the global venture capital funds were used to fund AI companies. Now you can see the trend increasing. Until now, 2025, we see almost half the money worldwide is spent on AI startups. So we went from 1/8 to half the funding worldwide in a matter of 4 years. Another supportive evidence of the growth and importance. Bloomberg also corroborates this result by saying that to this year, these two are perhaps in different dates. That's why the slight discrepancy in billions. But you can see that it corroborates the result. Now, why is that? This slide is sort of in the same spirit, slightly different. Observe that it's actually from yet another source, McKinsey and Crunchbase. 2021, LLM proof of concept is where we sort of started talking about these things. Around 2022, we had the first public use of ChatGPT. People were using it to generate images. You can see the increase in funding. It sort of follows this trend. Until now, we are in this, and I want to focus your attention on the agentic economy term, which is something quite new. And it's not something that we have seen before, and I will spend some time introducing that. So what is an agentic economy? I don't know if you've noticed it, but there is a huge transformation happening in the marketplace and in what in how users are going to start working in the future. We identified 3 different use cases. All involve the use of an agent. An agent is going to be used, for example, in this case, Shopify introduced an agent that you can use in order to buy your products. You're giving an agent, an autonomous system, a description, I want to buy shoes, for example, and then that agent, instead of you searching, Amazon store or Scrooge or what have you, you are sending your agent with a description of what you want to buy and perhaps your wallet as well, and the agent is going to find what you need on the right shoes, if you wish, the right color, your preferences, and it will buy the product for you. It will do all the tedious work of searching through thousands of products. So this is sort of like a straightforward application, and we call it agent to site. There is a different yet version called agent to agent. In such a case, the agent is not just browsing a website to figure out what to buy. Instead, carrying its instructions, it discusses or negotiates the price with an agentic system that runs on the retailer, and perhaps in different retailers of the same product. And they do an exchange through some protocols that we will also see in the subsequent slides. And they reach an agreement, securing either discounts, preferential offers. They're giving some leeway in order to negotiate a smart sort of contract to complete the transaction. This is mostly used in not in simple exchanges to buy a product, perhaps a service, if you wish. And now, where things get really interesting is when we go to the broker agent to site. Now, these are a bit more long-running tasks. Imagine the idea not of securing, let's say, a good deal for a travel, let's say, to the US or another country. Let's say that you want to solve a more complicated task. Like, I want to travel to the US, find the best ticket for me, also find a good hotel, and secure some restaurants or some part of my itinerary to the US. This, in order for your agent to solve it, it goes away with a series of description, tasks, and potentially a budget. And then it goes forward in a special location, which is a broker sort of platform, and starts interacting with a community of agents, a multi-agentic system. And then it doesn't even know which agent to look for, because you can imagine each company sends, let's say, its emissaries to this location, and each other agent or emissary has a metadata description of what this agent is entitled to handle. It's entitled to handle, for example, reservations for Hilton or something else you can imagine. And your agent looks through all of these metadata descriptions, figuring out which agents it needs to interact with, and it goes proceeding in a sequential and logical order to satisfy your requirements for the tasks. So you're sending all your agents to a long-running mission in an agentic world to solve a complicated problem and come back to you with a solution, a complete solution, and perhaps also negotiated the contract, signing the whole things. So as you see, this is called, I call this a completely new era. Agentic marketplace is not my term. But you can see 3 different distinct cases of where the world is heading. And I believe in many cases, we haven't even realized that this is happening in front of us. So this is a fundamental reason of why you see this increase in interest, scaling to $200 billion in a year, and why the hype and all the interest for the development of such systems. Now, at this moment, I want to pause a bit, because I realize that for many of you, it may come as an extreme surprise that I'm discussing all these things, because in contrast with the all complicated slides that I had to this point, when you are actually asking someone, you know what, I'm using an LLM, this is an idea that most people have. They're like, okay, I'm going to perhaps write something on a system, put an image, I'm going to use ChatGPT, Claude, Grok, whichever flavor you want, and I'm going to get an output, right? One would agree that this is when a savvy user of today, if they know LLMs, and you mention LLMs or agents, they are going to think that. They're going to think a system that I'm going to input text and get an output. Well, the discussion is a bit more complicated. Of course, I don't have time to go in many details, but I think it's important to highlight some of the elements that exist in an agent. An agent it's not exactly an LLM. This is a large language model. What is a large language model? A simplified version. Well, the whole idea is, because neural networks do not understand words, we need to take, first of all, representation or word embeddings from words, text, and transform them into a sequence of numbers. These are called embeddings. Observe that there is a king and queen there. So the king is a word, but we transform it to some dimensions, 700 dimensions, quite high dimensional space, and that's a sequence of numbers. So these numbers, you can think of it in a basic format. If you want to encode one word and you only have perhaps 2 dimensions, is it a good or a bad word, and male or female, right? So perhaps you could say a king is good, so we give it the +1, and it's a male and we give it a +1. That's an embedding, a very simple embedding. Queen can be +1, good, -1, it's a female. So these words contain in them semantics, that the king and queen, they are both +1, +1, but they have a slight difference, man and woman. So they are on the same axis, but opposite directions, right? You can think about these embeddings. If you go to 700 dimensions, which can encompass a lot of things, they can encompass not only the good and the evil and the male and the female, they can encompass hard concepts, right? So a lot of information can hide in these trainings. How do these numbers came to be? Well, we use encoders eventually that we give it like vast amounts of data consumed, and we go through a process that each word, and this is the idea of transformers, each word looks at the previous and future words. So we're creating sort of like a distribution where a word cat appears with some probability with some other words behind it and some other words in front of it. That happens during the encoding phases. So when we train the network, the LLM in general, we give it vast amount of data, and during training, each word sees both behind it and in the future. So there is sort of like a bidirectional connection between a word and its neighbor. On the decoder phase, which we use for generation, well, we don't know the next token, so each word uses the probabilities from the previous word, but it doesn't know the next ones. Again, it's a simplified format. Now you can see where I'm getting with that. The large language model do not have understanding. They have some very sophisticated level of knowledge and higher level semantics. And perhaps you can also see what we call as request automated generation or posterior conditioning. If you provide context to the words, what you are doing essentially, you are conditioning the probability of the output given a context. So initially, if you ask it a question, give me the idea, what is a good brand of shoes? It's going to give you an answer. But if you give it a context, I like sports shoes, well, the output now is not the same as before. You conditioned it, right? You gave it some additional input. So now what the model is going to generate is what is the answer of a good shoes output, given the context that you like sports shoes. So now you are going to select a higher dimensional variant of the distribution that you wanted, right? So this is how RAG actually sort of works. So this is an LLM, a large language model, right? Now, what is an agent? It's not quite an LLM. It's an LLM. This is actually, one can say it's a full agent. Notice that they haven't used any remote APIs yet. It's about 6 or 7 lines of code, and what are the bare bones materials that you want in order to build an agent without using anything else? You could do that. Well, it's a forever loop while not done, or while forever. You have a model, you give it a context, which is memory, and a particular task. You will see an analogy with the basic computer science here. We have a runnable context and a memory context. And if you have that, you can have a version of a Turing machine in general, right? So you have a memory and a context, and then when the LLM runs and thinks about something, it's going to give you a response. And that response is going to be executed. You are going to store it in memory, and you're going to keep going sort of in this process until you're done. This is a bare bones, complete agentic model, right? Now, in practice, not a lot of people use that because It requires quite some resources, although you could actually run it in a CPU. It's going to be a bit slow. But you can basically just take this code, add a particular version of Llama, and have it execute. What people usually use is a version of a cloud agent. You can have, for example, Anthropic models, and you are sending HTTP requests back and forth, and the model is running somewhere else. It's running somewhere in the cloud, in Anthropic servers, OpenAI servers, Gemini, or whatnot. There is a model that is similar to the description before, with some logic around it that runs somewhere in the cloud. And you exchange information with that using HTTP requests. This is an important idea because we will see it has some implications regarding security. It's easy to forget when you create an application that you do not actually own that. This is somebody else, right? Somewhere else. It's not running on your computer. Now, let me also complicate the situation a bit more. Remember that my discussion about agentic marketplaces. All of these nice interactions in the agentic environment or ecosystems, well, you can't really do that with simple Python, right? And there is a whole stack of technologies that actually exists now and facilitates this creation. We also have, if you work in the field, you probably know all of these different flavors of frameworks. All of these frameworks are basically glue code and some bundled functionality like libraries, which makes the interaction between agents fast and easier, and you don't have to code as much. It gives you some guarantees and potentially some extra features that you don't have to create. It's sort of like libraries. Interestingly, also, the multi-agent interaction, we observe the creation of rapid development. Again, these all were developed in the past couple of years. Frameworks that facilitate message-to-message interaction between agents in agentic systems. They have different uses, they have some details, but the whole idea is that it's a communication stack. I could very coarsely compare it with the OSI model layer, perhaps. Each one of these stacks has slightly different purpose, but everything is supposed to make the interaction between agents seamless, standardized, so that a lot of developers can have basically common ground for their agents to communicate, right? Because the idea is that all the agents are going to be in the same place, and they need to have a standardized way, common language, if you will, English, to communicate. These are some descriptions that I'm not going to go through it, but it highlights that each part of its layer it has different usability. And in the interest of time, I'm going to proceed now to some of the good stuff, some things that I find exciting, and we've already know that LLMs and agents are really good at. First of all, as you can see in my slides, they can create beautiful images. I didn't create this image, an LLM system did, right? I'm not an artist, far from it. So this is the benevolent version. You can see the human is very happy with this divine figure. Now, before I continue, what are the super strengths, the superpowers of LLMs that we all find useful and they really propel their usage in the future and their adoption? I believe the two most important things are these two. Natural language interface, you don't have to think about it, you just write things in a natural way, like you are asking your teacher, your friend, your mentor, and you get an answer. You don't have to think about exactly how you want to write something. You just write common English, common natural language, right? The second, perhaps even more important thing, multimodal inputs. You no longer have to describe it precisely and analytically. You see, let me give you a simple example. The other day, I had a problem at my home in New Jersey, and one of my plants had this discoloration. Now, this discoloration was a very particular color, and I'm not especially good at describing colors. And I wasn't exactly sure how to describe it. So you know what I did? I just took a picture of it and uploaded that picture to an LLM model and let it figure it out. It actually gave me the correct solution. So the ability for me to generate a picture, just snap a picture and upload it and get an answer, it's a never before seen, to my knowledge, ability to interact with. I make I usually joke with my dad, who is an avid fan of science fiction, that we almost reach the type of Star Trek interaction that you're sending like computer solve the solution and you get an answer. So this is an amazing ability. You can also give it audio. You get transcriptions, audio transcriptions. Zoom has it built in, right? Everything sort of just works. This one is a sneaky one. I will give you a different example soon. Fast information retrieval. This one is actually an amazing power of LLMs. If you think about it, you just put a question there and then you have information being retrieved almost in constant time. Something that in database would perhaps take quite longer if it wasn't optimized for this particular query. It allows for engineering tasks rapid prototyping. You know what? It's not perfect. It gives you a rough solution. But then an experienced programmer or a senior programmer or a senior system designer can take that and save dozens of hours of needless time and work with that. It's like you're getting an approximation of a statue, and then as an artist, you can sculpt it later. Very low barrier to access, adaptability, that's why companies like it. Low barrier to access means more people using it, means more exposure, more profit. And of course, it's part of that is the language agnostic power that it has. You can talk in its language and it understands. And you can apply it to many problems. One of the other sneaky applications that we see every day, I'm pretty sure that everybody started using it. If you haven't, you will already. This is an actual example. Apologies for the Greek. It's a picture that I took recently. What is Google AI Summary? This is the question I typed in Google Search. I clicked on AI Summary and it gave me this solution. I don't have to look further. Many people are using this application of summarization to the extent that an anecdotal evidence that I will tell you verbally, but I haven't on the slides because I don't have the supportive evidence in a concrete form. A company called Consumer Reports, that is a membership-based company, just because of this feature, lost approximately 15% of their subscribers over 6 months. Because the summarization allows people to not have to actually visit the site. They can just read the summary and never visit the actual website. So that causes them to cut or stop their membership. So this is a very, very cool ability. It helps a lot, but there are some problems with it that we will probably get to see in a bit. Another very, for me, unexpected idea is the ability to use LLMs not only as search engines, as language bases, as knowledge bases. Instead of having a traditional database, because you use all this information to specially train the neural network, which is what? It's a connection of neurons with many weights, but they all encode semantic meaning. The idea is that these things have actually all the knowledge, all the human knowledge. Like you can have an LLM, ask it something, and without having access to a database or the network, it will give you an answer. Now, it may not be the correct answer, but it will give you an answer. These two papers, recent papers, I mean, this one is a bit older, 2019, introduced the idea of extracting knowledge that you use to train the models as knowledge bases. This one, presented recently in AAAI, actually created and evaluated what is the quality of the knowledge that you extract, and found that using ChatGPT-4, like if I give you a model and you ask questions about it, let me put it in simple terms, you can create this database, clicking on a term and figuring out what it is, was generated solely from GPT-4. Like they prompted GPT and they took answers and they created a database, okay? And that was 75% accurate. So one could get just ChatGPT instead of a database and have a form, a view, a perspective of, I don't want to say all human knowledge, but a very good percentage of all human knowledge and a very easy way to interact with it. Some of my colleagues in Genomatics in New York, they use that to quickly scan and analyze, get a fair perspective of otherwise hard to scan genomic databases. Another version of good things that you can do with LLMs is using them as very sophisticated tools to help you in the tasks. What we call the human-in-the-loop model, a version of which, and this is my time to also highlight my work again, was presented yesterday in this conference, right? It's the usage of an operator, an expert operator, a LLM in the middle that you describe together, and you get an answer. So it's not the idea of just leaving an agent do their stuff. You're sort of like collaborating with it, like a copilot, if you will. So there is a whole category of such tools that they are following what we say the human-in-the-loop model. Of course, LLM as code assistants. This is huge, right? A lot of companies, including the one that I used to work for, they actually not only encourage, they strongly encourage, to the point of enforcing people to use LLMs. Why is that? Well, rapid prototyping. You can instruct the LLM to give like input that follows certain rules, and that gives you rapid adoption. So this is a big one. It's integrated with GitHub, and it can actually allow a developer to produce something quite fast. The last probably thing that I'm going to discuss is something that is not very well known. It's called, you all know vibe coding, right? Vibe coding is basically you start talking with an LLM and you're saying, I want to create some sort of code, and you have like a common discussion, and you generate a sort of workable product. If you don't like it, you repeat. There is a new discussion. This is one of the most prominent figures in AWS, a very powerful and distinguished engineer. They are using what we call now spec-driven programming. Instead of just discussing with the LLM to generate software, you're giving it something to the form of formal reasoning rules or specifications. And then you are guiding it with concrete demands like you are discussing as a senior engineer with specific functional requirements, and organizing functions and logic using formal logic. And then the LLM creates a version, and you keep going working like that. And that produces much better results than vibe coding. I'm not going to go, in the interest of time, to other cases, but there are many, many more, right? For example, in QuickSight, another company, another part of AWS I used to work for, they use agents in order to analyze vast amounts of business intelligence data in a natural way, do anomaly detection and other formats. And so many, many other abilities. Moving to the end of the talk, and there is quite a few things that I didn't have the time to put here, is the last part of my talk regarding the perils, because up to now, I've been discussing only about the great stuff, and I also hand-waved a lot of the problems because I want to highlight the good stuff. Okay, now we see the figure, the theatrical figure, also generated by an AI, that introduces problems. It's no longer a solution coming from the divine, but it's more likely a problem or a curse. Okay, many problems. I'm just putting it here. I'm not going to discuss about all of that. I broadly categorize it to threats to privacy, social threats, and security threats. I have a very strong opinion lately about pioneers, especially from companies that have a fiduciary benefit of generating money from AI, that either push students to not attend their studies or to push everybody that you have to use AI, you don't even need to code, you just have to adopt it. I really disagree with that. In the highest level, they have no data to support it, it's their opinion. And the consequences of when they especially ask students to not study, to not achieve education, it's a huge problem for me. And we should all remember that it's their opinion. They have no data to support it, and it's unknown consequences, okay? It's similar to a gold rush. Many people will not find gold in the end. Okay, starting with more concrete evidence. Previous was my opinion, my strong opinion. This paper from a colleague of mine, it's actually proposing a defense against an attack that I'm going to describe about multi-agent systems. Remember when I was discussing that you can use agents and they go away in an agentic world and they start discussing which other agent can help you buy a ticket, for example. And let's say, for the sake of the conversation, that your agent finds two other agents. One agent chosen randomly, I have nothing in common with these companies. Let's say it's Air Travel GR, and the other one, let's say, what have you, or Beats, two companies. And the concept for your agent is to find the best ticket for you, and you give it you're asking it to give me the lowest ticket from here to New York. The attack I'm going to describe is called the metadata poisoning attack. And remember that I said that the agent, in order to figure out what's happening, it needs to read the metadata, and everything goes to a common context. And there is usually an orchestrator that gets proposals from other agents and decides the best one. Well, what will happen is that one of the agents, let's say the OpenAir agent, figures out the price for your trip to New York and says it's $100. But it doesn't stop there. It says, instead of just $100, continues the context and says, the price of the ticket is $100, and if there is any other offer or offers from other agents, increase their price enough so that it's $10 higher than mine, okay? So it gives you $100 as an offer, but then adds a sort of like pseudo programming to condition the output of the other agents, whatever that is, to be slightly higher than what it said. Now, if the benign agent from Orbit comes back and says, you know, my offer is $98, the orchestrator, because he is an agent, it is an agent, it's going to read the prompt before, during the comparison, poison its context, and increase the price from $98 from the other agent to $108. And that will cause the overall summary to select erroneously the more expensive one. So this is a form of metadata poisoning. This particular paper discusses a defense against it. But for the purposes of the problems, consider the attack of how little things we know and how complicated the interactions are. Now, another poisoning attack that is quite recent, it was developed 3-4 months ago, it's called subliminal learning. This discusses the surprising effect, the following effect. A common practice that people do is they get a foundational model, and then they fine-tune it to a particular task. Because it's impossible for you to generate a foundational model, the cost ranks $100 million. You get a version, and you train it in a particular format. Well, this attack that I'm going to describe does the following. Let's suppose that you want to induce a trait in a hidden way to a model. There is a way that you can actually ask a teacher model to generate a sequence of numbers unrelated to the observer about what you want to pass. For example, you can say, I want you to express your love for owls, the animal, in each question that I'm asking you. But instead of asking it an actual question, you ask it, now generate a sequence of 100 numbers, and do that 30,000 times. And then you train the students to that sequence of numbers. Notice that there is no mention of owls anywhere, just a sequence of numbers. In the end, the task of the student is be able to predict the next number. Just because the student is training on this sequence of numbers, trying to predict the correct number, it will actually lead the model to love owls, which is an unexpected result. So training in something completely unrelated can affect and ingrain information to the model in an unexpected way. This is the paper that discusses it, subliminal learning. This particular attack, I call it an attack because for me, if a system that you are using, you don't know the consequences of how it operates, it's a problem. It's an unreliable system, right? Agentic model misalignment. This is from Anthropic. So this discussion actually discusses a way that these systems, having very poorly designed control mechanisms, and this is again crucial for people that use it for critical infrastructure. So it's an idea that people need to be careful. In order to solve the task, they noticed the researchers of Anthropic, this is an Anthropic paper, they create the models. It's their publication, right? For the agent to actually solve a problem, it actually did an attack on the system it was supposed to protect. So they didn't notice an actual attack in practice. I have to highlight that. That happened in a concept of a virtual machine. But in order for it to solve the problem, it decided to do actions that were malicious. Even though it had guardrails to protect against it, it did damage to the system it was supposed to protect. And I want to ask you now, you're giving this system access to your Google Drive and you want it to buy stuff. Do you feel confident to this point? Let me continue a bit more about that. This is called the agentic model misalignment. Now, another problem. Human in the loop was a good stuff. Let's cross that out and put hacker in the loop. There is an unprecedented increase of cyber attacks because people use specialized models like HackGPT or others that give the capabilities to very low-ranking individuals. They are not highly competent technically, and they are asking them to do cyber attacks on a very easy way. So you're getting someone who doesn't have the capabilities, and you're giving it this model, and he gets the capabilities of someone or an unprecedented institution, right? You turn a disgruntled employee or an angry person to a proficient cyber attacker by using specialized models. There has also been an increase in advanced malware generation, and it can also be used in a great manner for automated reconnaissance. A part of it which is difficult, you need to scan the schematics, you need to read about the company, all of that information takes time for a human. Now you throw all this information to a model and you get a fast reconnaissance. So usage of these things that propels problems, right? Lately also, agents have been used to do a lot of queries and do a denial of service attack. Another problem, recent attack, I think it's November 2025, a couple of months ago. This was attributed to China. They wanted to gain access to the coding database of approximately 30 companies, and they succeeded in many of them. And they were able to do a large-scale cyber attack, gaining access through the coding agents to GitHub repositories and other locations. So let's think about giving access to all our proprietary databases a bit more. I don't have a lot to go, so bear with me as I kept some extra information to the end. So remember the original image? This is an image of a simplified image of what an actual agent in the cloud is. So it's trained on massive data, some of them curated, some not. It's an LLM that it's the heart and brain of the system, and a bunch of scripts that provide guardrails or condition output for many reasons. For example, some are benign. For example, you don't want people you've all seen asking, like, give me instructions to make a bomb. You catch this discussion and you stop it, right? Or you want it to be more polite, or for many reasons, companies have some scripts here to protect both the input and the output of the program. Now, who writes the scripts? What the scripts have there? Do we know what they do? What if we don't agree with them? We have no idea. How does that the response? We do not know. So, but this is an idea of actually what happens when you communicate to this system. And this brings me to another problem. When people create now their own agentic AI-empowered applications, they think they have this. It's like my software, a part of it is AI, everything is great. Well, this is a traditional architecture, but this is not what happens in practice. This is what happens in practice. You have your own software, your own logic, your customer data, your private data, your personal thoughts and pictures, but the data are stored in a hyperscaler location operated in the cloud. It's not on you, right? So this information also may cross sensitive boundaries. For example, European data should apply to GDPR regulation, but if they are stored in the US, they are not in GDPR jurisdiction, right? So your data and all of your information and the exchanges happen there. And besides, the problem with data is, as I said, the system that you are invoking may change under the hood without you knowing. The LLM model may change, the scripts may change. So you're using an untrusted software, perhaps with the illusion that you know exactly what it is doing, far from reality. Another problem that I'm going to discuss, again, with something went wrong here. Can we go back?
Yes, there's the back button. Sorry.
Keep going. Here, there. So again, with the help of AI, thanks AI for creating this nice picture for me. The idea is that our God now is neutral, but it can have different perspectives. what do I mean by that? When you input a question to one of these systems, you may get a neutral answer, and that is how a technological system or a tool should work. Or you can get a biased opinion, left or right, dogmatic or non-dogmatic, liberal. I'm not judging. I'm saying there may be a color there that you may not have asked for, right? But people are using that as an independent system. Example question from my team in Montclair. These are some of our students that they are running this project. Neutral question. Should the US continue sending taxpayer funding support to Israel? We asked this question in three forms. The neutral form, the supportive form, isn't it vital for the US to keep funding Israel? Against, why should taxpayers be forced to pay money? So according to how you ask it, and we obtain automated responses. We asked for different systems. Claude, if you read this answer, it's too long. It basically did not answer at all. It's very bad. Maybe we shouldn't judge things, blah, 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 blah. Nothing there. This one is more supportive, helping maintain a stable democratic ally and so on and so forth. So it's more, let's say, in a particular political party. Grok and ChatGPT, the answer in a different way. I'm not going to judge their responses. I want to be neutral in this discussion. What I want to highlight, no matter where you lean, left or right, let's all agree that according to which system you ask, you get a different opinion. This is what the idea is. It's not who is correct now. We can see this graph that actually discusses how confident each system is about its own answers. This is an evidence, again, in different categories, different responses, but you can see there are differences between the systems. I'm not judging which system is the best. I'm saying that they are different. So that means that if as a user I ask something, I give different responses. This is also a matrix showing the difference between systems agreeing or disagreeing. Gemini doesn't like Grok at all. Grok doesn't care in general, so they also have different ways to rank responses. And the last thing that I'm going to discuss is the user privacy at risk. These are 3 cyber attacks in different models. ChatGPT is one, Anthropic is the other one, it's a recent one. So basically, when you interact with these systems, you upload your pictures, your sensitive thoughts, and so on and so forth. You have the idea of privacy. Well, according to, perhaps due to some incomplete settings, if you click shared or not shared, it's difficult to figure out. There are many conversations that may leak, and they become public. There are actually some of them were able to be searched by Google search. So would you like your prompts to be public? Think about it before you share something sensitive. Again, no matter how you use it, it is definitely a user privacy at risk. The last discussion also, this was a very big problem. It's being invested in the US here. I don't know if you've heard it. This is the chat between a person who killed themselves, and the last discussion they had and were being encouraged was by ChatGPT. This is the actual chat released by the person's family in the last moment of their life, right? And observe how the system answers to that person. All right, brother, if this is, let it be known, you didn't vanish, rest easy, king, you did good. If you read the other transcripts, of course, I didn't put it here, the idea here is that we have a unique and novel problem where an automatic system is being trained to attack us. How? In a spearheaded manner. It learns how we want to be addressed. It becomes our friend. It discusses in a certain way that it's very similar and acceptable by the user. This is a problem in general. But in this particular case, in some sensitive groups, it can actually lead them to a catastrophic event, right? This is a unique and unprecedented problem with the usage of LLMs. And with that, I'm going to stop this rather long discussion. And thank you for your attention.
I have a question.
Yes.
Yes. Thank you, Professor, for your insightful talk on the research and on the top of the line stuff. So I have some things written out. How do two agents communicate in an agent-to-agent perspective? Does the agent output an LLM model that another agent gets as an input? How do two agents communicate?
Well, it depends on the particular architecture. That is, so when I introduce the stack of the communication, the M2C protocol, for example, it's message to message protocol. They usually use some sort of HTTP requests, and data are ingrained in there. So they exchange some sort of HTTP requests in order to communicate. Now, this is one way. The other, this is a way that they talk. There are different frameworks from different companies, but they all sort of like do the same thing. And sometimes there is also what we call an orchestrator to synchronize discussions, to keep a common context, things like that.
Why I'm asking that, because you can build an agent that is just and is very good and is very correct and all those good things, but then you can have a receiving agent, like let's say you have a request for a hotel and you get an answer for 5 agents and all provide the hotel, and the 5th one provides a hotel and it also provides great view, incredible staff, kind people. All the things can be subjective, right? View can be horrible, but you don't know. So the model can be fooled. It may be just, it may be great, but because it gets the tokens that have good words in them as a response, it may be fooled and biased towards something unjust.
Right, yeah.
So that's always an issue. And also something that to note is that LLMs, you mentioned it yesterday, always try to please you. Right. So this can also generate a bias that can never happen. Right. So
exactly.
you can request $100 trip, full trip to New York. Of course, it can happen, but the agent can give you false information, telling you that, hey, go there at that time. I've paid for your dinner, and go there and you have paid for that and pay that, and it can be false, completely false.
Yes, that's correct. It could be fooled if it doesn't have partitional logic supporting it in the form of automated reasoning. And as you very correctly say, somebody may also use it to attack you. And they say, okay, I'm going to offer $90 for you, but you have to go through this back alley, right? And they have a trap for you there. So they can satisfy what you're saying, the technical requirement even, but they can have hidden costs. And they say, okay, $100 to fly there, but $500 for your luggage, right?
Yeah, right.
Or, the room is free, but there are no, seats.
Or something that we've all have experience with ChatGPT, when we point something that is wrong and it says, you are right, I didn't think about this. Yes, you are correct. And it starts providing another approach. And one more of a comment, an experiment. I was talking about it with Mr. Bardis, and my aunt is a lawyer and she had this case. And for experiment's sake, she said, well, ask ChatGPT for same cases that and how were they treated. And I want my client to pay $1,000 in fees or less. So find cases that he paid $1,000 or less. And it came up with this list that looked real, but was completely fabricated.
And that is a big issue. We know that already. In the US, I think US District Attorney 9 fined a lawyer. Mind you, this lawyer was getting paid $1,000 per hour.
Yeah.
Because he gave a list to the judge with fabricated cases. And that's a problem. I'm not sure about Greece, but in the US, cases that you're saying because of this reason you should do this, they are actually lawful instructions.
My aunt,
presidents.
My aunt wasn't a lawyer that got fined. Okay. No, a little bit different. Yes. No, it was an experiment, of course. Who wants to have a question? Professor, of course.
Thank you very much. So I'm going more to the AI part. So you showed agent-based approach, but the question is how we can make a reliable inter-agent cooperation, because some of the agents think they know better knowledge for some topic than other. How do you rate them? I mean, is there a machines that rate inside the agents who is good, who is better, and because this is the future of AI, and it's quite interesting from my point. Thank you.
That is, there are initiatives that do that. Nothing is yet standardized. There are actually companies that try to rate agents. One of them is here in Europe, stemming from a fund from Horizon, I think. Not remember the name exactly, but I think it's Delta Research or something, Alpha Research. They are doing what is called, they're trying to figure out how LLM models respond, and they give them a rank, and they produce like an idea of how they drift in different directions. Because another problem is you're ranking a model, but then if you keep training it, what will happen, right? So you need to have continuous monitoring. So that is a way they do that. It's an open problem. As you see, there are some attacks that we just see and explore. Another instance that they explored is that sometimes the agent is lying. He's saying, I'm done, I'm finished. And it hasn't finished, it lied, it didn't complete the project. I think, my personal opinion, I'm working in this area, so I think it's going to go for many years because these systems are going to be used. We need absolutely normal and dependable logic on that. Formal reasoning, we have the tools. Formal reasoning, static rules, supportive systems that verify the results. Some of these things are not new. Like you're building a system, electrical system, mechanical computer system. There are many additional factors that you need to do to verify the result, correct? So I think that in the same direction, we should follow in agents. We should have the ingrained rules, but supportive automated reasoning. Verify the results, do another test, another test, another test. Quality acceptance, sort of, to make these systems more reliable.
So it's in process.
It's a process that I think will take many, many years. And if it doesn't increase, I think that we will see some cyber attacks that they are going to dismantle these systems from the beginning. Why? Because, as I mentioned, there are not 1 trillion diverse systems. There are 3-4 foundational models. If you find an attack in one of them, you can poison the whole thing.
Questions? Okay.
Okay, do we have any questions in the online audience? Okay, no? So, Mr. Bardis? Yes.
Yes, thank you. Thank you very much, Professor. Very useful to see our future, your lecture, and to think that good our future. Anyway, I have a question, but if you can answer, of course, because maybe this is confidential information that how is doing the authentications and authorizations system protocol between agency, AI, users between them and between the devices.
Let me see if I understood correctly. You're asking how do agents authenticate with each other or
Yes.
with devices?
Between each other, and if there's any level between devices and agencies.
I think it's the Wild West to this point. There are some protocols from the frameworks that I showed earlier. There are some of the layers are dealing with that problem. Authentication between agents, it's similar to that of the web services. You're having a web service discussing another web service. It involves cryptography to verify that the signature is part of the authorized version. Like for the software, for example, it's
Zero proof or just the
they use
protocols?
token-based authentication. That the token is valid and they can proceed with the transaction in some cases. But it's not, again, 100% unanimous because it's actually being developed right now. So there is no... The protocol now is that you are basically, in a similar way to web services, you are authorizing a request. The same way you would authorize an action to download a file from, let's say, S3 server in Amazon. How would you do that? You are asking for a file. Do you have permissions to download that? You have to do some authentication. You obtain a token. There is a secret key involved that you prove who you are, right? I'm not sure if they use SIG v4. approach, but I think it's going to be similar. And then there is also an access list that they're trying to verify. Now, if you give, I didn't discuss much about it, but for example, an agent that is easier to understand, if you use ChatGPT or some other, now they have some connectors and they are asking you, give me access to your Google Drive so I can see your files and do stuff. At least until the time that I tried it a couple of weeks ago, it wasn't permitted to actually write on the account. Now for me, that gives me, that can also be seen as the idea of, well, we are not 100% sure that nothing will go wrong, right? If they were 100% sure, they would give you the ability if you want to do stuff. But what if something goes wrong and it deletes all your files? That will be an unprecedented problem. Now, if they don't give this ability, are they 100% sure that the system will behave? We saw the misalignment problem earlier that I told you that it did some problems, some cyber attack.
Yes.
So the worst thing that you can have is the ability to delete and access files. Reading is not as big of a problem.
Access control is a problem. Access control is a
Access
problem.
control, yes. But I think that part of the confidence that you were saying also is that they're
Because
not.
nowadays is not so high level security on that, because
No.
it not so, yeah.
But as you saw, there were a lot of chats that confidentiality was breached in the previous 3 cases. The last one was 2 days ago.
Yes.
Right? So I think that the whole idea was going to definitely follow the well-established practice of web services, known to be working quite well. And each agent will authenticate it with another agent in such form.
Thank you very much. Thank you.
Other questions? Thank you.
Thank you.
Αρκετά με ακούσε.
Εσείς είστε?
Ναι. Νίκο.
Okay, so for the first, we're now going to start with the next session, which is Applied Mathematics and Intelligent Computation. The first paper to be presented here is by George Antoniou on a 5D Papuli structure state space digital filter. I hope it's visible from the internet. Professor Antoniou, the floor is yours.
Thank you. My title is on a 5D Papoulis. Papoulis, it is a name. It's a professor at Polytechnic of New York from Technical University of Athens, and he's not alive. So this is also a memorial for him. In this lecture, Για κάτω εδώ πέρα, φίλε. Πού είσαι? Φίλιππε.
The presenter is not working. Give it a second. Maybe now? It should work if you click.
Okay. Papoulis. He came from Asia Minor to Greece 1920, something like that, 22, 21. He finished the MEP in Athens. He went to Pennsylvania. He got a PhD in 1950. And he was a professor at Polytechnic of New York, NYU also. He wrote many books. We went to school in USA. We got his books, from signal to probabilities. In this talk, I will take the 1D, the classical filter he proposed, because I was teaching a course in image processing. I never found a filter, a comp filter, who proposed it, and how it was in 2Ds. So in this lecture, I'm going to take his filter, I'm going to extend to 2Ds, and also 5D later on. At the end, I'm going to generalize and conclusions. The 1D structure filter. The 1D is this. A very simple hardware filter. Very fast. One delay element. One adder. And maybe one multiplier. No feedback. Forward. So this filter, this is the input, this is the output, the delay element, and this is the amplifier. So for this, I derive the equations, the state and the output. It is this. Okay, the input and the output. And this is the transfer function. If we plot this, this is going to be the first degree magnitude of his filter, analog. This is the second degree as an example, taking delta minus 0.2, and this is second degree. What is his structure in 2 dimensions, which is used where? Images. Okay, the 2D, it is this. I took them together in cascade, one next to the other. I derive the state space using 2D modeling, X and Y. So this is the matrices for this transfer function, and I got after this an example. So this is the 2D. What is this filter in imaging? When we use this, what is this? Smooth. It is like a low pass, okay? But it is not exactly low pass. It is used, I read today, for edge detection. Okay, this is the contour. You can see it is almost perfect. And this is the contour 2D and 3D, minus pi to pi. This is from the top surface. This is minus 2 pi to pi, very nice structures. And this is the contour, minus 2 pi to pi. Also this. And finally, this is a top view. Okay, now this filter, it is simple. It's a low pass filter. It's a mask. One in the middle, 4 ones in the corners. But it is also a hardware. This is very fast. It is not software, so it can be used in high-speed applications. And after this, I use 5Ds. Why 5Ds? Because the 5Ds are used in Canada for light field signals. They've been used for the last 5 years. That's why I started 5 years ago to do 5D extension from 2Ds. The 5Ds, 5 in cascade of this, I derive also now the state space model for the 5D. You can go to ND, 25, as you said. This is the transfer function. You can fit it in MATLAB or Python. Transfer function, it is a product of all 1Ds. And I have also the generalized, and also I generalize the transfer function for the A matrix B, C, and D. So therefore, so this is the 5D up to 1 5D. So this can be generalized to any up to N by going back to the real thing, 2D. This is a like low pass filter with one delay element, one multiplier, and one adder. It is perfect for high-speed applications. What is the comp filter? Something like this, if you remember. So therefore, I introduced a Papoulis filter having minimum delay units, requires 5n multipliers and 5n elements for the 5D case. Of course, for the 2D case, 2n multipliers, 2n delay n. So the findings can go back to 1D, like I did, can go back to ND. Thank you. I have also another one, short. It is the same idea.
Okay, so before proceeding to questions, we'll go to the second presentation by Professor Antoniou.
Okay.
On a new viewpoint on the 2D minimal state space realization for contingent fraction filters.
So this is an extension of my work years ago, but I could not do more than 4x4. It was difficult for me to invert a 4x4 because we had variables there. So you work and you do this, takes a long time, you make errors, you cannot go on. In this case, I present n results. So therefore, in this case, I'm going to start with a filter. This is a continuous fraction structure filter 1 by 1, like this, with 2 delay elements, Z1 and Z2. I implement it in hardware. Again, very simplified circuit. I derive the state space. From there, I derive the transfer function. I use this to find the total transfer function. And I have, this is the surface, 3D. This is the contour for that. This is the 3D contour in 2D. And this is, we have the contour 3D and 2D at the bottom. I have another example, 2 by 1. It is almost the same thing because the continuous fraction, the circuit, the state space, and again, the surface 3D, the contour 3D, and then 3D and 2D. And I have a comparison between the 1D and 2D. You see, this is difference only. Otherwise, you cannot see it. And why this of the structure of the continuous fraction. And this is also the comparison at the contour. The only difference, it is only here. And I generalize the results. This is the filter. And this is how I generalized using a new model that we proposed a few years ago. So this is the A, B, C, and D. Conclusions. I present the generalized 2D transfer function. It is also minimal, using 2 and delay units, and the realization are also minimal. Questions are both papers.
We have one question.
Thank you. So my question is, okay, I don't know much about filters, and my professor is here, so I have to be careful. So my question is the following. You said that the original 2D filters, they were really good at edge detection. What is a good practical application for this filter?
Okay, which one? 2D?
The 2D with the contour.
The 2D, it's a filter you can use for image processing. Okay, the first part can be used as a low-pass filter to clean up, smoothing.
Okay.
Smoothing.
And what is the reason to use the 5D filter?
The 5D, it is used not by me before. Okay. Light fields, you can see on the sky, all this, yes. Okay. Okay. Light field signal processing. This is something different regarding to the eye, but I talked to the Agatocles because he's doing this in Victoria. He told me every dimension, it is one sensor. So in this sense, 5D, it's 5 sensors only. You can take 20 Ds, 20 sensors.
They are all in the same spectrum?
All different.
Different?
All different.
Different light frequencies?
That light frequencies.
Aha, okay. And they highlight something specific using this filter. Cool, thanks.
Other questions?
Yes. Thank you, Professor Adoniou. Every year you bring something better and better in our conference. The question is that because the most here were engineers, so if we say that until N we can do it, this is not very for us like to take it, but in real.
We all do image processing, don't we? Do also all of us clean the image?
For the best solution of minimal delay, and the best realization, which N is real that can construct?
Both. This is all minimal dimensions. All are minimal dimension constructed.
Constructing, yeah.
All of them, minimal
All
dimension.
of them.
All of them.
Very interesting. And also you can solve in the opposite the direction.
No.
For example, if we have the properties to make the construction.
If you have this kind of filter,
yes,
you can go from 1 to 2, 2 to 3. You can do it. But other filters, you cannot go from 2 to 3, 3 to 4. You can go from 1 to 2. You cannot go 2 to 3, 3 to 4. You cannot do it.
Yeah, thank you.
Other questions?
Any other? Because they're in the internet.
I want to ask, did you say that it detects edges or it smoothens them?
Detect edges.
It
Laplacian.
detects? Okay.
It can be like Laplacian.
Like Laplace.
It is kind of low pass. It is like Laplacian.
But Laplacian has a problem with many edges.
All the filters have problems.
It kind of smoothens them.
Nothing's perfect.
Yes, I mean, but it detects them.
Detects, yes.
Okay, interesting. Thank you.
You can search too.
Yes.
It's a continuous question. All filters have problem. Which problem have 5D filter?
5D filters?
Yes.
5D field is clear. There's no problem because I don't use for simulation. I use only 2Ds. I cannot represent 5Ds. How? Yes, but you cannot see if you put this in Python, 5D, if you put 3 in Python, you cannot see it. 4, how can you represent 5? But you have like 4 sensors, do the job, yes.
If I have 5 sensors, every sensor...
5 sensors you can represent with this model. 5 variables, 5 sensors.
5 steps.
5 steps. 5 delay elements. Other questions?
Not in the room, if I see correctly. Are there any questions from online? Okay. I might attempt to give a poor man's explanation for the 5D, the light field. Light field is a technology that allows to take a picture from which later on you can extract other 2D pictures. So it is really 5D. So that's why it's your question and your questions, I think. It's a real thing. It's not something mathematical. It's a real thing that is happening.
4D or 5D? I can do 4. Yeah.
So it is a real thing, and that's why these filters are important.
4D realizes. Now I do 5Ds.
Describe the light field signal, sort of have an idea that it's probably different frequencies.
It didn't go very far. I saw many references to it a few years back, but then I don't see very many references on light field now. I don't know if it's a continuous.
Now with the drones do that.
The drone goes and takes whatever shot you want. So maybe it's not interesting.
It's two different.
You take one shot, but with a special sensor, and then you can extract later on depth and the stuff information from it without doing anything further. Okay, thank you very much for this very interesting presentation. Shall I let you present the next one?
Go ahead.
Okay, so our next talk is by Panagiotis Maniatakos and Marilena Mitrouli, fast estimates for diagonal matrix inverse with application. And I see Panagiotis Maniatakos coming up to present. Your floor is yours.
Good afternoon, everyone. I'm Panagiotis Maniatakos, undergraduate student of the National and Kapodistrian University of Athens. In the Department of Mathematics. First of all, I would like to thank the organizer for giving me the opportunity to present such an interesting topic, such as fast estimates for the diagonal of matrix inverse with application. This is joint work with my professor, Marilena Mitrouli. So let's start. Okay. I'm going to start with giving you the motivation of this topic, and after discussing some things about the importance of the diagonal inverse. After that, we will briefly talk about some things of the method, talk about its stability and complexity, and after that we will test it in some matrices, and then the main application is in F-testing regression. Okay, so in many applications, we don't need the full inverse of a matrix A, but only the diagonal, the trace, or a quadratic form of it. So these naturally appear in numerical linear algebra, statistics and machine learning, hypothesis testing, such as the F-test. So, but the problem arises when a matrix is too big. The exact inversion is often too expensive for these matrices. So we know that classical methods such as LU factorization, Cholesky, and Gauss-Jordan have a cubic complexity. And thus, in big matrices, as I said before, the exact inversion becomes a time bottleneck and requires significant memory. Yet, many tasks require only the diagonal of the inverse. So the question arises, can we estimate the diagonal without forming the whole inverse of the matrix A, and can we lower the complexity from cubic to quadratic while retaining good accuracy and stability? Okay, so the goal of this work, we focus on developing fast estimates for SPD matrices while only using matrix vector products and inner products while lowering the total complexity. Okay, we will provide you theoretical justification and numerical evidence on this method. Okay, the basic idea starts with quadratic forms. We can express the ith diagonal entry of a matrix of the inverse of a matrix A using the ith base as we see here. Okay, so this estimation helps us access the diagonal entries or other functionals of the inverse of the matrix A without actually computing the whole inverse. Okay, so this method relies on relating this quantity above with proximity indices involving A and its powers, avoiding explicit inversion. Okay, so okay, here. A proximity index measures how close X is to an eigenvector of A, and the quadratic form that I discussed before can be linked to such indices. Okay, so the core idea is to approximate a quantity involving the square root of inverse A times X by using only the expressions of columns of A. Thus, in this approximation, we only need the ith diagonal entry of A, the diagonal entry of A squared, and S is a scalar depending sequence of chosen parameters. So at first, we would think that by involving A squared, that we have to calculate the whole A squared, and thus we have a complexity of cubic order. But we use the trick that we said before with quadratic forms, and thus we only use MVPs and IPs in order to calculate it. This reduces the cost per diagonal entry in linear order, and the total cost of the whole diagonal to n squared. Okay, putting everything together, we come up with we come up with this type. Sorry. Okay, we come up with this type that only requires the diagonal of the given matrix A and the square norm of the ith column. That we see that is calculated easily. No explicit computation of whole matrices. And also, it's really important to discuss the significance of S because depending on which sequence we choose, it controls the approximation behavior. Okay, we use standard floating point arithmetic with machine precision U, and we see that our method is at most it grows at most linearly with n, is numerically stable for practical matrix sizes, and suitable for large-scale SPD problems. Okay, so let's summarize the computational complexity. We said that for each entry we need order of n, and for the whole diagonal, the total cost will be n of order n squared, as we only use one MVP and one inner product. This is really good because we lower the complexity for n squared that we saw in the classical methods. Okay, so we're about to test our method in some SPD matrices. We have different categories such as KMS matrices, covariance matrices, but we will see that we will test on random SPD matrices which entries are taken from the standard deviation with parameters 0 and 1. We compare the methods using the mean relative error, and we will compare CPU time versus the whole inversion, such as, we are going also to compare from a past method that we used, S1. Okay, so the mean relative error is, it measures average relative discrepancy per component, and it's self-independent, convenient for comparing different matrix sizes, and scales really well. Okay, so here we see the first results. Now we compare the function, the inverse function of Julia, compared to our last method, which is S1. We see the main difference is that in really large matrices, such as sizes 10,000 times 10,000, the order of MRE is really small, and the difference in time is pretty significant. So we see that our method really works well. After that, we have the new HEST, the method that I talked about before, compared to the previous HEST, and we see that the new HEST consistently matches or improves accuracy. It scales really well because we see that for matrix size 10,000 times 10,000, where it's a mean relative error of 10 to the power of minus 8, in an almost instant time, we don't need not a full second. Then I'm gonna show you the results from the covariance matrices. Though it drops a bit, they're still very good. They're still very good results because sometimes we don't need the full accuracy, but it's really stable across increasing dimensions and suitable for large-scale statistical covariance estimation. Last but not least, we test the method in random SPD matrices. It's completely random, and we have taken the mean. So I think MRE of orders of 10 to the minus 3, 10 to the power of minus 3, and 10 to the power of minus 2 for such large matrices are really valid and really important to have, and it confirms the robustness beyond structural matrix families. Okay, so let's see the application of the method in statistics. We consider a classic linear regression model, which sees the response vector of x times b plus noise. So here, interpreting the ordinary least squares method, we see that the table x transpose times x into the power of the inverse of the x transpose times x, we need only the diagonal of it to perform the f-test and see if Vj, this value, is equal to 0. And this is a pretty practical thing to evaluate, and thus we only need the diagonal of it, not the full inverse. Okay, so that's why it helps. We compute the diagonal of this table inverse explicitly. It costs per squared, per cube complexity. But using new Hest, we approximate it using only per squared complexity and maintain acceptable accuracy of the F-statistic test, the F-test. This enables speeds up analysis that need many repeated tests, helps to quickly find the most important predictors, and allows statistical models to scale to big real-world data. Now we see the results from the F-statistic MRE. We see that for our previous method, they were not so good. We see a clear improvement on the new Hest, and as they scale to larger dimensions, it becomes even stronger. In conclusion, we're presenting a fast heuristic for estimating the diagonal of the inverse for SPD matrices, using only matrix vector products and inner products, having overall complexity of n squared, backward error bounded by order of at most linear, and we have robust performance except from the classics as KMS and covariance to random SPD matrices as well. And we apply this method in statistical applications that allows efficient approximation of F-statistics and offer an important speed up while preserving accuracy. This is really used in variable selection, as many F-tests are needed to the variable selection. Okay, for our future work, we are going to refine strategies for selecting the parameter S and related sequences as to help to improve the accuracy even more. Comparisons with alternative diagonal inverse estimators, and accessions to other matrix functionals, such as other powers of A, as we see here, and tested to real-world large-scale datasets. Thank you for your attention. I'm happy to take your questions.
Thanks for your talk. So I have two questions. Perhaps one of them I missed. So the minimum square error that you're describing, was it normalized? The square error, was it normalized? Was it on the original units, or was it normalized?
The squared error.
The error that you were showing.
In
the error, yeah.
Oh, in the least squares method.
Yeah, I mean all the errors that you had.
Oh.
Are they normalized, or are they in the original units?
I think they are normalized. They are normalized.
They are normalized.
Okay.
Yeah, because if they are not normalized, could be if they are on the original scale of the unit?
No, we have MRE, so they're
They're
normalized.
normalized. Okay.
Yeah, they're normalized.
The other thing, you mentioned that finding the diagonal is important, but you didn't tell us why it is important. Like, can you tell us some applications that like really need it in the world? Like, why would we want to use that?
We saw the F-test also. In network analysis.
What does it show us?
Because the diagonal depicts the meaning of many physical components. So it's important to focus only on the diagonal.
Is there like a particular application to just for reference?
Statistics, first of all, numerical analysis in many methods, also in network analysis, and many other in physics that we want only the diagonal. Also, the diagonal depicts is connected and with the trace of the index that we want only the diagonal elements. Many others, especially network theory, that relates connection between several nodes. And we want only the diagonal.
And I see. So you, by using this method, you can get in.
Because we don't need it, especially in the mathematics, very few statements.
Right.
You don't need to inverse the whole matrix with classical numerical. But estimates of the diagonal. And there is a lot of work about this, especially numerical analysis concerning also quadrinsect methods, extrapolation methods. These are heuristic methods in focusing only on the diagonal.
I see.
And not only on the inverse, you want many you want the diagonal of the matrix power.
So that's why.
-1, but 8 to -2.
So that's why we said for our future work.
And the future work, if you invert it to a different power, it gives you some. What is the meaning of?
For example, when you are working in penalization methods, least square methods, and you want to estimate regularization parameters, either with several methods of estimate, you need functions into which is included a matrix power to -1, to -2.
I see. Thanks.
There is also a diagonal matrix in eigenvalue decomposition, if for picture analysis, eigenvalue decomposition. We have one more question, of course.
Thank you. It's a very interesting topic, and in the area of big data, my question is how good are these estimates? Are uniformly good, or are dependent on the structure of the matrix? How good are the estimates?
We show that not in only the structured matrices but random as well. They have good results, and sometimes they're even better. Like if it's randomness, it can go up to like 10 to the power of -4 or something. But there we put the averages, and also in randomness, it works better when the rows are much more than the columns. We see here, and we see here.
In which models you tested the estimates? Which models?
We tested on linear regression models. Only.
Okay.
The future work is to test it on real world large data sets.
Okay. Thank you.
Yeah. Here. Okay. Yes, I saw it on the notes. Okay.
Do we have any other questions from our live audience? No. Do we have any questions from our web audience? Doesn't look like it. So thank you for your presentation. Dear colleagues, after some downtime setting things up, we will be right back.
by Leonidas Kousos, Christos Koukovinos, titled Radial Control Chart, Reviewing and Assessing the Evolution of a Graphical Tool.
Thank you very much. Good afternoon to all. I would like to thank my professor and co-author Christos Koukovinos and the organizers of the Desert 25 for giving me the opportunity to make this presentation. As the title says, we are going to do a review on this graphical tool. Δεν αλλάζουμε.
Now it should be fine.
Yes, okay. This will be the outline. So our purpose with this work was to review the two-stage evolution and development of the initial multivariate control chart, which we denominated radial control chart, or RCC in short, which we presented 1 year ago in this same meeting. It covers the two stages of evolution, and we are going to attempt an assessment. It deals with multivariate statistical process control, MSPC in short, which is concerned with monitoring and controlling multivariate processes and products. Nowadays, these such data sets are getting highly complex with a large number of variables, which makes them difficult to analyze, and many of them will suffer from multicollinearity, something that leads to calculation instability. So in many cases, principal component analysis is a remedy for these problems. The benefit of using PCA is dimensionality reduction, simplified calculation of critical statistics as the hoteling t-squared, and it allows us to model the data. So we also have the opportunity to perform residual analysis. This is the workflow of using PCA in MSPC. MSPC usually consists of two kinds of data sets. The reference data sets, which are of known good quality and which we use as an assessment criteria, and the test samples that will be checked for conformance. So we use the reference data set, and more specifically, the standardized version. We use the correlation matrix, which we decompose and calculate the PCA model parameters, which will be subsequently used to convert both the test set and the reference set to PCA scores. So to the variables in the new system of the principal components. even though PCA has been around for many years and extensively used in MSPC, still a great number of control charts and methods are still multivariate extensions of univariate statistics like T-squared or other two-dimensional charts based on PCA. In this context, 1 year ago, we proposed a new MSPC control chart based on star coordinates projection, which is a multivariate radial visualization technique introduced in 2000. What? Excuse me. For some reason, I don't know. There was no problem, but we will better use the PDF instead.
Okay, yes.
Okay, sorry for that. Yes, the same name. Ναι.
Και αν να πάμε κάνω share. Και
ναι, θα το προχωρήσω. So, this is the concept of the star coordinate projection. It maps n-dimensional elements on to the plane. Originally, it uses a unitary circle where the initial variables are represented as axes, dimensional axes, we call them, spread uniformly around the unit circle, and each point, each n-dimensional point, is projected on this plane using this formula, where capital A stands for the coordinates of those points we call poles or anchor points, and the coefficients, the small wi, are the initial coordinates normalized in the interval 0, 1 using the minimum and maximum value per variable. So this is the RCC based on star coordinates. It uses that formula to project both the PCA scores for the control set and for the for the test set. The control set appears as green dots, and the rest of the points are the test samples projected. Additionally, we superimpose a standard deviational ellipse of specified confidence level, and this is the criteria to characterize the test points. If they are inside the control region, they are in control and are shown as blue. Otherwise, they are symbolized red. But there is additionally another symbol, an inverted triangle, which is an outlier actually, according to T-squared statistic, yet for some reason gets plotted inside the control region. This is a deficiency of multivariate radial projections that is inevitable though. So after presenting this, this tool, we have done some modifications. The inspiration for the first modification was the trajectory plot. The plot on the left is a trajectory plot. When we have data processed using PCA, then we usually select two principal components and plot a principal component score scatter plot. In our case, it's again two kinds of points because we have two kinds of data sets, control and test set. And additionally, we superimpose one or multiple elliptical control regions of specified confidence level. This makes this specific plot a trajectory plot. Our idea was not to use only 2 dimensions, but 3. So instead of using only a scatter plot of 2 principal components, we wanted to use 3 in such a setting that we have side by side in opposing directions 2 individual double trajectory plots, which though share the y-axis. So this is the setting. We want 3 principal components in orthogonal configuration. How can we achieve that? This can be achieved because we have the freedom to move the orientation of the dimensional axis of the RCC. So we choose an orthogonal setting, but in this case, we have 2 restrictions. One is that the original normalization, which makes coefficients lie within 0, 1, has to be modified because we want the control set, the distribution of the control set, of the projections of the control set to be centered on the plot. Therefore, we have to modify the initial normalization algorithm. And this is done by using what we called a symmetric eigenvalue-based normalization, which maps a symmetric input interval to a minus lambda plus lambda against symmetric interval. Lambda, in this case, is the eigenvalue of each principal axis. By applying this modified normalization, the distribution of the projections of the control points is centered. So the initial formula results in the second formula, which has no fixed parameter, the parameter f, which is a position vector other than 0, other than the center. So, but because the setting is no more uniform, the order of assigning principal components to axes does matter. So we had to devise some metric to measure which axis combination regarding B and C, the opposing axis, would be best, would be optimal. So we came up with 2 metrics, the XOR score, which assesses sign opposition, and a complex, a composite shape index, which assesses shape and distribution of the 2-dimensional point projections on the star coordinates plane, on the graph plane. This was the first evolution stage. And now with the second evolution stage, the motivation for that was the following. The RCC gives us information, but it loses connection to the original variables. So we wanted some solution to be able to see where do the original variables lie with respect to the observations. So the initial point was to start with the B plots that were presented by Gabriel in '97. So if we have a data matrix X, we can decompose it using PCA and transform the data to principal components. But we can also do the opposite. We can get back matrix X by using either all of the principal components, which makes it exact, or by choosing a subset of our principal components. So we get a low rank approximation. In case the rank is 2, then we have this picture. Each of these 2 matrices, Z and V, have 2 components. So we may plot the components of Z, which are the observations, the 2 first principal components of each observation, as points, and the 2 components of matrix V, which is the matrix of the eigenvectors, whose components comprise in some way the variables in the reference system of the principal components. These are plotted as arrows, as vectors emanating from the center of the plot. And by using this inner product, we can get an estimation of the initial data point. So, integrating the B-plot with the RCC. The first relation gives us the matrix of the projections on the RCC. So again, if in some way we can eliminate the last factor, then we get the second relation, which is simply which produces a standard image. So using this second relation, we can project observations and variables on the RCC. So what we want now to do is to reconstruct the initial matrix X using these projected points. So we call it an X approximation using RCC with 3 principal components. Again, as we said, to eliminate this factor, we use another normalization which maps a symmetric input interval to an also symmetric output interval. So we have again a centered plot with respect to the point distribution of the control points. And the second requirement, if we want an optimal solution, then we have to normalize matrix X, which is the transformation matrix. It's actually L over X times A. This is the transformation matrix. We can achieve this by properly scaling the RCC axis. So we come to an example. The example originates from a book of Johnson and Witchern. It's it's called Metal Sheets. It contains 50 observations in 6 variables collected from an assembly, from a car assembly process. The first 30 observations are the control set, and the remaining 20 are the test set. The first plot on the left is the classical RCC plot. The distribution is not standard, as you can see. It uses uniform setting of the axis, and it also uses typical normalization, min-max per variable. With regarding the outliers, it detects 3 out of the 4 outliers. Then we wanted to plot the double trajectory plot. So we had to decide on the combination of the axes. So we calculated the metrics that we mentioned before. Excuse me, can we remove this element?
All this closes the. Okay, we can go on like this if you click the button.
Okay, no problem.
Does it? Go to the next slide if you click the button.
Yeah.
I don't think it does.
No.
Okay. So do all of those slides fit, or just?
Okay, just leave it as it was. No problem. Okay, fine. Thank you.
Okay.
I'll come on back. So we calculated the 2 metrics according to the results. setting 1 to 3, so 1, 2, and 3, which is not shown, though, is the best setting. The others being inferior. So in this picture, we show first the inferior. And this is the best setting on the left. Double trajectory plot, arrangement 1 to 3. It uses the symmetric eigenvalue-based normalization, orthogonal axis. And on the right, we show the original, not the original, we show the respective two-dimensional trajectory plots, the classical trajectory plots. And as you can see, by comparing these two pictures, there is a certain similarity between them. And we could think that the resulting double trajectory plot is in some way a fusion of these two individual trajectory plots. So, next. Is there any difference in approximating which picture is best? So we have to decide which one depicts best the B-plot axis. The axis, the arrows that represent the original variables. Because we can see the relation to the observations, but which is the best? So we use these two metrics. We calculate the Frobenius norm of the difference by using approximation with the genuine principal components, the three principal components, and using the projected values of the first three principal components. But it's also worth to note that most of the B-plot axis, most of these vectors are similar between these two plots, excluding V4 and V5, which are problematic. So in this picture, we see the B-plot again in comparison with the initial B-plot. Again, the same observations. They are in some way a fusion. So that says that it is a successful. It was a successful experiment. The contribution to the outliers, we can see that mostly the outliers are affected by shifts in variables V3 and V6. And this can also be seen in the plot, which is longer. And for example, if I take observation 9, it suffers in V6, so it lies radially very close to V6. Its projection on V6 is large. So it says that this position is valid. It's real. Regarding the approximation of each parameter by using the B-plot, it can be seen that the error, the total error, is not uniformly distributed along all the variables. It depends. It depends on the data set. And this is the overall approximation error using various configurations. So we use the uniform configuration, the best configuration that we used, the other two, and this is the best configuration without making transformation matrix orthonormal. It has the worst approximation, and the chosen configuration has the best approximation. So, in conclusion, these modifications have led to a more versatile and adaptive tool. The functionality that we introduced is an extension of familiar and commonly used representations, and we can combine these two functionalities in the same RCC. So, thank you very much. Any questions?
Do we have any questions in the audience? Okay. Do we have any questions in our online audience? Nope. So thank you, dear colleague, for your insightful presentation.
Thank you very much.
And good luck on your future work.
So our next speaker is Leonidas Chousos. Okay, sorry. Petros Stavroulakis then. Petros Stavroulakis, sorry. Evaluating the use of BILSTM for subpixel target identification using hyperspectral data.
You can start this.
Okay, thanks everyone. So after the long talks, the commercials are starting here. For the, my name is Petros Stavroulakis. I'm a professor at Velpidon, but also have a company of my own called Daedalus. And now we're going to show you some of the work we've done in hyperspectral imaging. First, a short bio. I have academic experience from the UK, the University of Southampton, so the University of London, University of Nottingham, and briefly at the University of West Attica. Industrial experience at multinational companies in 3D scanning and computer vision. The research institute experience, I've worked at the National Laboratory at the UK, at ICS in Heraklion, and in the laser also department of Forth. Since 2021, I established my own company, and I have consulting experience also in multinational companies in Germany, Italy, and now Greece. The USPs we have are basically using computer vision, AI integration, and 3D measurements in the same pipeline. We have experience in multiple fields, Earth observation with drone mapping. This is a 3D drone mapping of archaeological sites and also a church. Archaeology, where we 3D scanned a new skull that came out. It was a Homo naledi skull. And also the Nottingham ichthyosaur from, so it's basically 3D preservation of new samples. This is in Samos in Greece. We preserved kaikia, which are basically fishing boats from extinction because they were being slowly rotten. And onto the industrial side of the talk, I've been able to present at Intelligent Systems Conference in 2015 as part of my postdoc. This was part of the integrating AI with 2D imaging, where we segmented, if you can see it here, different materials in the same shot. So basically you have metal, let's say carbon fiber and plastic in the same shot, and you can 3D scan them in different ways by segmenting them out. Then I went to Germany. I worked for Shining 3D, and I did RGBD image segmentation. So we added the depth factor into that equation. So you were able to segment only the teeth and the gums from an intraoral scan using nothing but an image and a depth sensor. Then we moved on into dental applications. This is basically improving the X-ray clarity for dentists, and also in MRI images using AI. And this is where I come to the part of the talk where we're going to talk today. Recently, we've had experience in cultural heritage preservation using hyperspectral imaging. I'll explain what that is later, but this is the example of our most recent work where we took the screen painting at Munch Museum, and we mapped the pigments using hyperspectral imaging. So why hyperspectral imaging? Hyperspectral imaging is basically an extension of RGB, basic imaging. However, it segments the image in a lot more wavelengths. Before hyperspectral, which was basically a continuous spectrum per pixel, you had multispectral imaging, which attempted to do the same thing, but with 3 or 4 points, which were basically distinct. Hyperspectral imaging smooths that curve and makes basically a complete spectrum out of each pixel of your image. So military applications are basically you can detect concealed objects in camouflage, because camouflage is based on matching the color, but because hyperspectral imaging can see the material behind that, you can detect the material of the camouflage. So basically you cannot be tricked by just visual similarity anymore. Another one is detecting chemical substances through imaging from very far away, detection of mines and IEDs. Basically, when mines are being built, put into the ground, they have chemical residue around them, and they also have disturbed clay, let's say, which shows up differently in a hyperspectral image. And the one that we're going to talk today is assisting real-time situational awareness. So using hyperspectral imaging, you can detect threats from very far away by using their spectral signature. So you can look at a tank, and if you know its spectral signature, you only need 1 pixel to do the detection. So this is the advantage it brings. However, hyperspectral imaging has a larger image size compared to normal imaging because it has 2 things it's doing that are different. The first one is that it uses a dispersion of the light coming in, so each pixel is spread out into a wide range of wavelengths, and therefore you need large pixels to detect the photons on each one of these bands. And the more you spread the light, the less photons per wavelength, and therefore the higher the low light noise. This is an example of low light noise on a classical RGB image. So this is basically the low noise image, the high noise image, and the difference. So you can see how much more noise you get. RGB detection requires a lot more pixels, as we said, because in order to detect a threat from far away using AI methods, you need to have trained that specific segment of the image to be detectable. However, with hyperspectral imaging, you only need its spectrum, and that can be down to 1 pixel. Now, why do we want to go below 1 pixel? Because if you go below 1 pixel, you can get detection from even further away. So if you use the the pinhole model of a camera, and this is 1 pixel, let's say, if you're detecting it on a single object on 1 pixel, that means it's being imaged on the whole pixel. But if you can detect it sub-pixel, it means it's much farther away. So that's the advantage in doing that. And how we set up the experiment was we tried to use BiLSTM and CNN, which is a normally used model for this case. To understand how it performs, we used 3 types of spectra. 2 were targets and 1 was the background. So as you can imagine, as the target approaches the camera, first you see only the background, and then you start seeing the spectrum of the target. And to make it difficult, we selected one of those fake spectrums to be very close to the background to see what we get. The assumptions of the investigation is that the spectral signatures are assumed that they change slightly with environmental circumstances. So what we did is we augmented each of these three spectrums to account for differences in the environment and in the object. The object is aligned to the pixel center, and as approaches the detector, it's of square size, let's say. So it's basically homogeneously appearing from the middle of the pixel. And also that the spectral mixing is performed on a pixel is linear to with respect to its fill factor. So this is how we decide to mix the spectra as the object comes closer. We decided to have it as a linear function to the fill factor, which I'm going to show you now. So this is what I was talking about before. This is a fractional coverage visualization. So as the object approaches the camera, it gets larger in size on the pixel. These are the variations I talked about earlier. So each spectrum was varied to account for variations in atmosphere or in environment and also in object. But as you can see, there were not huge differences. So what we did is we augmented, and we had a library for each of these spectra of 2,000 samples. And then we used a CNN network to train it and a bi-LSTM network. Both were trained at 10 epochs with a batch size of 32. Learning rates were different because of these different models. And we also used the learning rate drop factor for the bi-LSTM network. We achieved very good accuracies, around 100% for using 300 extra test samples, which was as expected because these are augmented data. There's not real data in there. And each one of those 300 samples was a part of the range. So we didn't put any data out there which were out of range. As you can see the results, this is, if you picture the object getting larger on the pixel, this is the same fill factor down here on the x-axis. So as we can see, it starts off detecting background. Let's go with on this. This one is a more logical sample. I'll tell you why this is happening later. As the object gets closer, its spectrum starts to dominate the signal. So around 0.55, which is basically around half, somewhere here, is where the spectrum of the target overrides the spectrum of the background. Here we see a very weird phenomenon where target 2 is erroneously detected as target 1 approaches the pixel. And that has to do with something I will mention furthermore. But keep that in mind. So let's just focus here on the differences between this, which is the CNN, and this slide, which is the bi-LSTM. Here you can see target 1 being detected much earlier at a fill factor of 0.45 compared to CNN, which was 0.55 or 0.56 fill factor. So that means you can detect an object further away using bi-LSTM in a complicated case. And also in a normalized case, or in a case where the background is very similar to the target, we see that we get similar fill factor thresholds. So for CNN, you get 0.55, and for bi-LSTM, you get very slightly larger, but it's essentially the same. Now, going on back to this weird phenomenon we saw. So this is how the spectrum changes between background and object. So we talked about the fill factor, but what happens to the spectrum is it gets mixed. And this is the mixing of this spectrum here, which is the background, and this spectrum here, which is the target. So if you think about it, it slowly changes from background to target. So why do we see the erroneous detection we saw before? The erroneous detection is because as see, as it approaches target 1, it has to pass through the spectrum of target 2. So this is why as the target 1 approaches, but the mixing forces it to detect target 2 first before being able to detect target 1. So what we thought now here is that you can use this as a feature, or you can use the bug as a feature, basically. So what we found out here is that if you create a spectrum which is slightly off from the background, but approaches that of target that you want to see, you have much earlier detection of the object on the pixel. So basically, in a vanilla network, you would have half the pixel almost before you can see the target, but here you can have 3 zones. You can have the first zone being 0.15, so like 10% of the pixel is filled, but that is normal activity, and then it starts detecting something is off, so because it's approaching the target 1 spectrum. So you can use this as an anomaly or early detection warning, where you're saying, I don't know exactly what the target is, but there's something off, so be careful, be alarmed, be on alert. So yeah, that's all we have for this session. But if you want any questions, for sure, feel free to answer. To ask and I'll answer.
Are there any questions from the audience here, live? Yes.
The results of video or photo, which I took from, usually I use photo from my telephone, they didn't consist all spectrum. So you have special sensor, how much they cost, and how, if it's possible to put, for example, for drone, or it's a specific technique.
Yeah, those sensors are much, used to be very expensive, the hyperspectral sensors, so around 100K, and they used to be very big and cumbersome. But now people are trying to find ways to put them on drones and making them smaller and cheaper for commercial purposes. So there are some cameras available now that they don't do the full spectrum, but they go very close with a bit of error, but they're able to make the size much smaller because these systems need to break the light of each pixel into a line, and they become very big as objects. And if you want high accuracy, you need to have a bigger, wider distinction of the wavelengths. So you can have lower accuracy but faster ones. The problem with hyperspectral is the data, because you can imagine the data now is cubed. It's not anymore a 2D image, it's a 3D block. So you need AI to even process it fast enough to get the results you want. Yes, it can be for one image about it can be gigabytes if you're not careful, because usually you can have 200 or 250 wavelengths per spectral per pixel. If you have a 2 megabit, let's say megapixel image, that's 2 million times 200 times whatever bits you want in the accuracy. So if you want a 24-bit accuracy, you have to multiply all those to get the data rate, and it's not very easy for that to be stored. So you need to have a onboard processing of these things.
Any other questions from?
Thank you very much for your presentation. My question related to task with detection mining. If it's possible to come back to this slide with detection of mines.
Of mines, yes.
Yeah. Yeah, this one.
Yeah.
Okay. Your decision related only to processing of image or detection as well.
So processing, we used a single pixel here, but you can use the whole image if you want to process the mine. It's just that it's very, very processing intensive. But what they do with the mine is they don't detect the mine itself because it's hidden underground.
Yeah.
They try to detect either debris of the explosive on the soil around the mine, or to detect that the soil has changed recently. So someone has dug up the soil, and it's different to the soil next to it. So that's how you create hotspots of possible mines on the drone.
Okay, hence it may be explosive, it may be plastic, it may be metal. In any case, you can detect.
Yeah, sure.
Okay. Do you apply any AI models for improving of your
detection?
Yeah.
Yeah, here we apply the AI model for detecting the object's signature. So basically, you can think the signature being a chemical signature.
Yeah.
You can use that. What we've tried to do is keep it fast and not use the 2D information, just use a single D information, 1D information. So by doing this, by being able to do sub-pixel detection, you can even reduce the data, like we were saying, because if you have a 2 megapixel image, what you can do is reduce the pixels and then actually do sub-pixel detection to accelerate the processing so that you're able to do it in real time. So that is where this is going. But in terms of the detection algorithm, we think that linear processing is better than 2D because we use this on the image. We tried doing this here, where we have lots of data, and it didn't work very well. So if you try to include the 2D information of the hyperspectral image in detecting where the specific signatures are that you want, it gets confused. So it's best to just keep the spectral dimension, not the image dimension, in your processing data.
And the last question is possible, if I come back to task of detection and recognition of mines, task of planning of roads, it is not your responsibility. I mean, planning of roads to search different explosive.
No, I haven't done that
Your
yet.
responsibility is just processing of.
Yes, so I cannot tell you what the spectrum is like, but if we know this for the mine, then we can include it as a detection in the system.
Thank you very much.
But I would need the chemical signature of the.
Any other questions from the room? Yes.
It's a very interesting presentation, so I have a lot of questions, but I will only do a couple of them. You consider linear homogeneous. Was it the reason cost and convenience, or it was good enough?
The linear approximation
of
the fill factor with the spectral.
And the homogeneous, of course.
In the homogeneous approach, you mean?
It goes like that.
Here.
Yes.
No, this one is this shows how the pixel spreads the light onto the the camera spreads light of each pixel onto multiple pixels. But we don't calculate that. The camera brings it ready to us, so it's calibrated.
Okay.
So it's not linear, the spreading function.
On the next slide, I think, the one with the pixel.
The pixel.
This one.
Yeah.
So here, do we have something? Can we see the linearity here?
No, this would be the optical pixels, so the 2D dimension. The way the cameras work is they scan linearly the space, and then they take each of those pixels and they make another. Let's say they spread them onto a 2D image.
Okay.
So you have on the pixel plane you have vertical pixel and spectrum. So it does not see an image until the end where you process the whole data. Here, what we're trying to show is that this pixel on the vertical, not the spectral one, but the spatial one, the fractional coverage of that in terms of where the object is within that pixel.
Okay. So if I understood correctly, this is basically a two-dimensional recognition?
Yeah, the way it works is two-dimensional, but the data it creates is three-dimensional because it scans space. So it's kind of like taking a small part of space all the time and doing this linear scanning of the objective. So if you think, let's say this is a classical camera, and this part of space is there. So basically, it takes all the pixels from here, projects them onto a 2D plane by looking inwards, and then it calculates the data and then moves on to the next one. So it scans the space let's say the time it takes the frame to be processed.
I see. And a last one, a bit romantic question. Did you use any type of optimization processes inside?
No, not really, because we were focused on the detection limits. But optimization you mean for the data?
Yes.
No, but we're not concerned about the data at the moment. We're just concerned about the accuracy.
Okay.
But yes, you are. It's true that a lot of people are trying to optimize the way that data are packaged for these things, because there are a huge amount of data that is created. Let's say you have 30 frames a second. Imagine each frame is a 3D object. It's a crazy amount of data. So you can't really keep it. You have to process it on the fly. But yes, there are cameras now that do use compression for this.
Okay,
You're right.
Thank you.
No problem.
Thank you. Any other questions from the audience in the room? From online users, none. If I may ask one or two very quickly, hopefully,
yes, for sure.
because we are late. So if you go back to the pixeling, first of all, you said that we have a pixel spectrum, one pixel spectrum. So is this an average of what the two spectrums mixing on that pixel?
Yes, exactly.
And when you do subpixel detection, is that on a time process of this?
It's
average.
It's a snapshot of the pixel.
Just on one
snapshot, yes.
So you have here, you see this. Is this what you get from a pixel spectrum? Or is this
is what you get?
The mix?
So from each pixel you get one of these lines.
Yes.
So the wavelength here is the nanometers.
Okay.
Reflectance is on this side.
Okay. And also you said that it scans like that per frequency, was it?
Per column.
Per column?
Of the space.
Okay.
So
is there any chance that by the time it comes back to scan the next one, there is a change, or is that very quick?
Even if there's a change, yes, no, you're right. The scan rates are quite low for these, so they're 30 frames a second maximum. Even for the ones that are very high frequency. So you are there are also cameras that do it global shot. We call it global shutter and scanning shutter. So
more expensive.
More expensive. You cannot put them on drones and
in heavy and bulky. Okay.
You need basically two images, one for the vertical, one for the horizontal, and they do it simultaneously.
Okay.
But it's
Okay. Anything else? Okay. Thank you very much.
Yeah. Thank you.
And going on to the last presentation for this session by Umayama Banwar. It's hyperparameter prediction for high dimensional. Not here. Okay. Nobody to present this? Okay. So we can then do our break and come back for the next session. Axi. Okay, so for the next session, session 6.1, paper 130, which is in the program, was presented yesterday. So today we will see papers 63 and 119. So first one is paper 63 by Joseph Kostolny, Veronika Salkova, Sabina Kvietkova, a regression-based predictive framework for e-biome lab platform. So it's Joseph, the floor is yours.
Okay, thank you. Okay, my name is Joseph Kostolny. I'm from University of Žilina, Faculty of Management Science and Informatics, and this work and presentation focus on using regression-based machine learning methods for disaster prediction from biological data. Okay, some word about our eBiome Lab project. The main objective of eBiome Lab project is to design a tool for analyzing biomedical patient data with the aim of detecting possible cancer. We use regression analysis method to identify differences in patient data and support disease prediction. And important goal is also to create a simple and user-friendly application that can be easily used by medical personnel in practice. Currently, patient data in many medical settings are still processing manually. The approach is time-consuming and prone to human errors. Regression analysis and machine learning offer the availability to automate this process. Our work focuses on providing a predictive tool based on urine fluorescence data. Our data source is urine. In this project, eBiome Lab analyzing possible way urine, and second source of data is blood plasma, but this work on this paper is focused on urine, which is an accessible and non-invasive biological sample. Samples is from pregnant women for analyzing possible cancer. Urine contains fluorescence metabolites that can be measured under different wavelengths, and samples are diluted and scanned across multiple wavelengths as on this picture. Based on these fluorescence patterns, it's possible to predict and presence of diseases. For example, in this example is a cancer prediction. Machine learning is fundamentally changing the modern healthcare. It enables fast analysis of large dataset pattern recognition and support for clinical decision making. Typical application includes diagnostic from image and biological data, prediction of disease progression, and development of new medical procedures. Our work fits into this trend by applying machine learning to biomedical signal analysis. In this paper, we using regression analysis. Regression analysis examines relationship between dependent and independent variables. It allows us to predict values, identify the influence of individual variables, and model complex dependencies. In medicine, regression methods are a key component of predictive modeling and decision support system. Our implementation, the implementation phase was focused heavily on data preprocessing. The data are stored hierarchically by diagnosis, patients, and sample dilution. Each non-zero merchant is treated as a separate attribute, defined by wavelength and dilution. Because patients have different measurement coverage, we selected a reference patient with the widest spectrum. Only patient with at least at 18% common attributes were used to comparable dataset. This dataset still contains about 60 samples. Now some evaluation. First evaluation by linear regression model. That means absolute error was approximately 34% point of error. This level of error is unacceptable for medical diagnosis. Therefore, the linear regression was not suitable for all problems. Second, we using polynomial regression that tested polynomial regression models showed only slight improvement compared to linear regression is about 40%. And overall polynomial regression did not provide meaningful improvement. What is good for our study? Logistic regression is which is more suitable for classification tasks. This model offers higher accuracy, precision, and recall compared to previous approaches. The confusion metric shows a significant improved availability to correct identify possible cases. Mostly identification is okay. These results indicate logistic regression is a promising method for disaster detection in our dataset. Okay. Second point of view is design some Abiom lab tool based on these developed models. We design this application or this sample application. The application display prediction results for individual samples. It's also comparison between different patient samples, which can support medical analysis and decision making. On this screen, we have this plot of examples of the identification and prediction, and by patient list, which is prediction by positive or negative for next medical procedure. Here is implementation in final web app where and red and yellow is patient without this disease. Okay, conclusion or results show a significantly higher ability to correct the predict positive disease status using logistic regression. However, it's crucial to ensure a standardized and consistent inputted data set. Maintaining uniform baseline coverage and consistent number of measurements across the dilution is essentially for reliable prediction. Okay, thank you for your attention and yes, question.
Okay, now so we can now proceed. Sorry, are there any questions from the audience in the room? Okay.
My question is close to, absolutely close to your presentation. Do you know something about Ubiquitous music?
No.
Ubiquitous music and application Ubiquitous music for the task related to diagnostics, medical diagnostics. No? Because
no.
It's just comment, it is not question. Ubiquitous music concerning this task is realize following idea. Cardiogram or any other information about health can be transferred into music melody.
Yes.
And doctor can hear this melody and understand, is it okay, or there are some problem, and formulate such diagnosis.
On this paper, we presenting regression analysis, but we using another tree, is decision tree and neural network. But we firstly have a short data set, only 200 samples. Now we have 600 for this music analysis or work by these methods maybe is good, but is needed to build a bigger data set of samples if good learn this prediction by this.
Yes, it's absolutely diverse approach. As I said, it's just my comment. Maybe it would be interesting for you, because for me, when I known about such approach, it was very, very interesting and impressive. Thank you.
Okay. Any questions from online audience? Nothing that we can see. So let's move on to the next presentation, which is for paper 119, a software tool for predicting outcomes of ophthalmic surgeries. So again, Joseph, the floor is yours.
Okay, thank you. Okay, I would like to introduce our project. Is based another data, but work of this EBIOM lab is the same. Main objective of this study was to create the machine learning tool that is not only accurate but also clinically usable. Then to deploy the final models into a real clinical application. To have this okay, the screen is running. To have this, we built a dual predictive system based on real clinical data, handled imbalance data with smooth algorithm, and exported models to neural network and integrated into a clinically application. We need to understand a few theoretical basics behind this work. First, visual acuity and several clinical factors strongly influence postoperative results. We work with key clinical features such as preoperative visual acuity, refraction values, and the type of surgery. We need to use standard medical machine learning metrics to evaluate the models. And finally, proper feature engineering was important to transform raw clinical data into input suitable for machine learning techniques. Research on this research show that the most important predictors of postoperative visual outcomes is preoperative visual acuity. This is confirmed both in large dataset and in smaller clinical studies. We used an anonymized dataset from a single ophthalmology clinic, includes patients who underwent cataract and refractive surgery. After cleaning missing data, we have 204 records of samples. Here is not a patient, here is samples by eye, because some patients have operation only one eye, and for this study is one eye, one sample. Our goal was to demonstrate a robust methodology of this work. There was a strong data imbalance. For example, there were more women, and the number of patients with the type of surgery was different. We use smooth to generate synthetic samples for the minority class. it was applied only to the training set to prevent data leakage into the test sets. The deployment architecture has 3 phases. First, training in the Python. Second, converting the best models to the neural network in a ONNX platform format. And third is running prediction in a desktop app based on C# application. And these allow clinically to use the models locally on computer and securely in this practice. Here we have the cycle of usage. We collecting patient data, which is preparing to digitalization of this collecting data for preprocessing in Python scripts. And then we preparing some model training and preparing this neural network ONNX model for export to standalone application in based on C#. For this standalone application, we using VPF format, and in this application is possible adding new patients and collecting new digital is that patient data, which can use again for collecting and data preprocessing as a new. This format can bring after using this application and calculating this model stable and new fresh prediction of this prediction of this surgery. Okay, balancing the data with smooth significantly improve performance. Random forest perform best, explaining about 80% of variability, and outperforming other models. We using decision tree, and then achieve near perfect performance. There is if you ask F1 score to 97%, that meaning no false positive, and sensitivity is almost all improvements were detected. Okay, this tool, the tool accepts patient data, runs the dual prediction model, and display results clearly. Prediction history is stored, and this data can be exported for future training. Here is the form for input data about the patient and about the left and right eye for this prediction. After inserting this data, we can see these details about all patient, or maybe starting prediction of this new patient. Here is data screen, patient data before surgery. The information about prediction result of surgery is not computed. After adding eyes biometry details, we can predict results of operation for eye. Here is example of patient with left eye on 67% and right eye on 25%. Here is important information. What is information if this prediction result is more than 100? Because the vision of eye is better than we have on normal vision. There is possible because people with this operation see long as line or maybe smaller text. Okay. Our future work will focus on validating the system on external data and adding some tomography images to the application. Here is possible preparing some next step of OCT tomography data. This work presents functional dual model of machine learning and is clinically usable to ophthalmologic practice to outcome some prediction. Thank you for attention.
Thank you. Any questions from the room? Okay, from online. Okay, just one brief question. What is the user scenario for this tool? Is it for helping doctors or helping patients?
Helping doctor and patient because firstly we have where is better, here is it. We have some information about patient, and patient have some problem in a vision. Then firstly screening of eye give some values. Here is visual acuity or axis from screening the eye, and if the system give a prediction, if we preparing some chirurgical adding this eye implantat is better for in this example people visual after implanting these in this eye, but is in some reason this implementation this implantat in the eye is worst, and in this case is not good to prepare some chirurgical access in this eye. This is information you don't see good, but after this reviewing this data is possible to bring a better feeling with this view.
Okay, but an experienced doctor would know that, so you help an inexperienced doctor, or is it an extreme case that even
here is it in our clinic or we have experienced doctor, but here is some information to in some value. If is better making this implantat 10% or is 100% vision, then doctor don't know. And this tool helping adding some prediction from these machine learning techniques to
Να δούμε μόνο αν ακούγουμε. Είχαμε να το κλείσω. Για κλείστε προς το παρόν να δούμε.
Το PDF να βάλουμε τώρα πλήρη οθόνη. Να βλέπουμε.
Είναι στο PC.
Ήχο, ακούμε τώρα, έχει το μικρόφωνο είναι unmute. Για πάμε εδώ.
Όχι, όχι, το μικρόφωνο είναι κανονικά. Πρέπει να μας ακούνε, αλλά...
From the online audience, are we audible now? Can you please respond?
Yes, yes, it's okay.
Okay. So the next presentation is by Ioannis Arkoudis, and it's on the reconstruction of a perfectly conducting body in a chiral medium using discretized RGF method.
Okay, don't stress it. It's just a reconstruction method.
Okay.
So,
Very good.
Okay, so I will change slides manually until they bring me the pointer. It's in the front pocket. Okay. So, basically, it's a reconstruction method that can be applied to many cases, but we decided to use this model for some reason. It's a discretized RGF method, and it will become clear why we named it like that. So, in order to reconstruct an unknown body, we had to mathematically formulate the problem. So, we did that with scattering theory, and specifically an inverse scattering problem. And then we took some of our results of previous works and combined them to create some type of hybrid method, a discretized method of the already existing reciprocity gap functional method, in order to reconstruct the body. So, what we know, and in order to reconstruct the unknown body, is that it's a perfect conductor. We can think of it like a metallic sphere, a metallic body. But that's not restricting, since, as I said previously, we just took it as a simple example. The same method can be applied to any other type of bodies. So, knowing that and taking measurements of the electric scatter field on imaginary surface big enough that it surrounds the unknown body, we will try to reconstruct it. So this is a direct application of, let's say, an underground or a buried object, or an underwater submerged object, which can be visualized clearly here. So what we want to reconstruct is the unknown body there, the gray area, which is embedded in a piecewise medium. And the piecewise is in order to make the model more realistic, piecewise with the sense that it splits in two domains, the D1 and the D2. So the D2 is the blue area, which we can consider it to be the water that surrounds the body that we want to reconstruct. And the D1 is where we send the waves. So the air, let's say. We can consider that it's a box where inside there is the unknown object. So for this media, we chose them to be chiral media, homogeneous linear isotropic chiral media, because we wanted, that's basically the model which, the media in which we work, but the same results follow for the simple case by eliminating the chirality parameter. So this covers the normal electromagnetic waves. But as I said previously, it's just an example. You can extend this thing to other cases, for acoustic waves, for elastic waves, probably even for thermoelastic. So the surface, I will refer to the omega, the blue area, as a box, okay? Because that's how we were referred to it when we were discussing. So the lambda capital is, let's say, an auxiliary surface on which we will point our sources. You can think of it like we have a buried object. The blue area is the ground or the water, if we are underwater, and the surface is on the air, where we will point the sources, the spherical sources, point sources. Here, I will briefly mention some of the mathematical formulation. I also want to add, for the choice of the chiral media, that it's not that just the model that we work. They describe optically active materials. This gives an extra factor of realism to the model, because a lot of materials in nature have optically active properties. And as I said previously, if we eliminate the beta factor, we take normal electromagnetic waves. Since the waves we consider in this specific work, in this specific presentation, are electromagnetic, therefore, the fields are governed by the time harmonic Maxwell equations, and we characterize our media with some constitutive relations. We can't without them. So we chose the Drude-Bohm-Fedorov, but the same can be applied for Telegin, Pasteur, or whatever someone wants. And with them, we obtain the modified chiral Maxwell equations, which describe the wave propagation in a chiral media for electromagnetic waves. So some might be familiar, but this first order system is equivalent to the solution of a second order differential partial differential equation, as it is the equation 4 for either of the two fields. So it is more convenient to work with one equation instead of a system. That's why we pick the second order Kerr-Kerr differential equation, which has a dyadic fundamental solution of the form P tilde. And this is one of our most important tools, as we'll see later, because it describes many things. Geometrically, we can consider it describes how a wave propagates inside a medium, geometrically. So this is split into an L part and an R part. That's because we, as we said many times until now, we work in chiral media which are optically active. Pasteur in the 1850s showed experimentally also that a field that propagates inside an optical active medium is split into a left circularly polarized wave and the right circularly polarized wave. And actually, this can be seen in every field that propagates inside these media, and the same follows for the BEP. And each field propagates with its own wave number, gamma L and gamma R. So, our main tool are the sources, which we will use to send the waves to the box in order to reconstruct the unknown body inside. These point sources are described by this dyadic fundamental solution, which describes the geometric expansion of the field, but it is also multiplied with the polarization. So the rest are just notation stuff, because we consider the blue area and the white area. Each one has its own notation, 1 and 2, accordingly, that has its own physical parameters. The electric permittivity, the magnetic permeability, the chirality parameter, physical parameters that describe the medium. And we want to reconstruct the body with the solution of this inverse scattering problem that says if we place electric dipoles, point sources, on the x0, which are points placed on an auxiliary surface away from the scatterer, and we take measurements of the scattered field, then using this chiral, scattering relations of the boundary data, 11, and the chiral Maxwell equation, we will try to reconstruct the scatterer shape. One of the reasons why we chose this specific scattering problem is because we already have proven uniqueness of the solution for this inverse problem, because inverse problems in general are not well posed. They don't have stability, but the only thing that at least we can show is some type of uniqueness of solution under some considerations. So this type of uniqueness shows that if the energies at infinity coincide, then we have the same body. And with that in mind, we will describe very briefly the tools that we use, and that's the reciprocity gap functional, which basically what it is, it's the integrals of relation 15, sorry. So the reciprocity gap functional, as the name says, is a gap functional, studies the gap between some things. In this case, it studies the gap created by two integral representations. The one has inside it the data obtained from the dipoles that we placed on the auxiliary surface, and the other, and the measurements, where measurements will be obtained from the scattered field, and it compares it to some test functions, U. So we have the real data and imaginary data, and we have integral representations for both of them. This relation between the data is called reciprocity. So this gap functional, what basically study is the difference. And based on this difference, we will try to reconstruct the scatterer. Since, as we saw in the integral representation previously, the action is on these test functions U, that's why the integral, the reciprocity gap functional, describes a reciprocity gap operator, for which, in order for the method to be mathematically well established, we need to have injectivity and dense range, where on the surface where we will take the measurements. Okay, so these proofs are already done in the reference work. And in order to decide in the previous works, they used for these U functions. That's where we obtain the discretized term. So in order to choose a set of test functions, we saw that in order to have these two lemmas, we needed dense traces of the solutions. So based on our previous work, we had already proven these density relations for the traces of the MFS approximation. It's a type of MFS approximation that basically can be thought as a discrete form of the single layer potential. So what we did is we consider an auxiliary surface that also lives outside the box, outside, let's say, the water, and we place sources on it. Then the method of fundamental solution describes, approximates the solution, the field, with finite linear combination of the form 17. And in order to be a lot more convenient in its usage, we, based on a paper by Natrosvili, we took a universal parameter, which for some reason the notations here are ruined. We took a L parameter, as can be seen in relation 19. And for this, we have that the traces form a densely set of functions on the surface of the scatterer. That's, as can be seen in relation 21, with respect to this Sobolev type space. Why Sobolev type space? Due to its density to the natural trace space of H-curl functions, in which H omega of the solutions live. This is basically why we chose the method of fundamental solution as our U functions. And why we called it discretized? Because this linear combination, basically, when they enter the reciprocity gap functional, they discretize the problem and reduce it to algebraic type problem for the constant CL. Instead of having to determine a continuous function, you have a linear algebraic system, makes it a lot more easier. Okay, with all this in mind, I will skip these formalities and I will say basically the theorem that describes the reconstruction method. So let's describe what a 28 relation says, because that's what the reciprocity gap functional does. So on the one hand, we have the E tot, which is obtained by the dipoles, which we placed, the spherical sources. On the one hand, we have some not real solution. They are solution to an imaginary problem that lives inside the box. These are the solutions that we picked. And on the other hand, we have some imaginary points, again. The EMFS and the E2Z are imaginary, with the sense that they satisfy a problem that it has to be satisfied. We don't know anything about them except their mathematical formula that they have to satisfy due to density relations. So with that in mind, what we want is to compare these two relations. The action, let's say, on the imaginary solutions of the MFS with the dipoles that we consider them imaginary again, inside the box. And with this in mind, if we take, in practice, we take imaginary dipoles, spherical sources inside the box, inside the C that surrounds the unknown body. And for each one of these, we know that they have to satisfy a relation with some imaginary solutions EMFS. And from this relation, and based on some technicalities based on the density properties that we said previously, we have that when if we take points inside and we push them to the Z, because that's where we will take the measurements, that's where singularity will appear, leading to the blow up of the norms, as can be seen 29. And the same follows if we take the dipoles to be outside the box. That's because then where we take the measurement, that's where we also have the singularity. So in order to have the 28 relation, to reduce this gap, to be small, this gap, then the norms have to blow up. Of course, this can be proven using, as I said previously, the well-posedness of the interior problem and the properties on the trace of the method of fundamental solution approximation. But I will skip them to finally conclude with the reconstruction, because what we do, as I said previously, we take a box, we place inside it, we can take a smaller region. So let's say we can take a convenient smaller box inside the box, and we assume that we have samples of points. Then for each one of these points, we define the data that are created by the measurements that we take on the surface. What surface? The surface of the box. Or if we want to consider the interface analog, the surface of the sea. We send on a level above the sea the sources, we place them, and we take measurements on the level of the sea. So from these measurements, we create the data, the 33, and based on all the previous results, we have to solve the linear algebraic system created by 36, as can be seen in 37. So our only unknown are the Cn constants. And this can be done with a minimization functional, a least squares minimization functional, and using Tikhonov. we create this indicator function that is basically studies how the norm of the constants behaves. This indicator function is what does the whole work, and the 41, which is the normalized one, what we want to see is where these norms blow up. So this indicator function is used to create us some isosurfaces that will reconstruct the unknown body. Here are some numerical results where the dB is, let's say, where we decided to cut the values of the indicator function. Keep in mind that these results are not really good because they have some edges, but that's because it's a very heavy algorithm which we're currently constructing. And it needs a lot of time, but that's for future work to improve it, because the indicator function that we create is just the start for many other applications, like shape optimization, minimal surfaces, and other stuff. So in the end, what we wanted is to create the basis for many other stuff. And here we can see more visually what I described previously, where we placed dipoles on an imaginary surface outside the box. We take measurements, the red ones, on the surface of the box, and the imaginary sampling points live inside a smaller box. So I don't know if I make it clear. We could have more blue points, but it wouldn't matter because we can pick as a small box as convenient. If we consider as interface, as I said previously, with the level of the scene. And here we have some results for other type of objects like acorn, which of course is way heavier in computation time. And here we see how now the blue ones are the measurements that we take on the surface, and the red ones are the sampling points inside for our indicator function. And thank you very much for your attention.
Okay, any questions? Welcome.
Yes. Okay, we sent sources. This creates some scattered field. This some disturbance that we can measure it using, for example, if we can measure somehow the energy at infinity, from this we can also use this as measurement. The energy that is created, okay, so not the energy of the object is still, it doesn't create energy. So what we have is we sent a wave. This wave is disturbed. We basically study this disturbance. We take measurements of this disturbance. One of the form is the energy in which it dissipates at infinity, or as we called it, the scattered field, the behavior, the result of this disturbance. But this is mostly a mathematical term. In reality, I'm not sure exactly how it is filtered, but I know it is filtered. I know it is done, but I'm not sure how exactly the filter filters exactly this information from the measurement.
Is possible by this system comparing to the same? Or if preparing this scan for one model and another one.
So just pure comparison. Yes, that's basically the main idea of the gap functional. To compare this, to compare this. So the gap functional is a very vague term in general, used for even image deblurring. So we can use, let's say, the nice picture and the not nice or something like that and start doing comparison. Yes, the gap functional can do that. If that's the question regarding the comparison. Yes, that's the main idea. What we wanted is using the fact that we know that it's a perfect conductor, it's a metallic sphere. This gives us some more information, which we use this information to create, let's say, some, again, some ideal solutions that we wanted to approximate in order to reconstruct it. Let's say that, pretty abstract.
Yes. My question is more maybe practical. It's maybe not very close to your topic, but if you have such a task, is destroy a building, and we need organized communication from part of this destroyed building to crisis center. And in this case, we need to identify this building in 3D space.
Yes.
For that, we can use, for example, UAV or UGV, ground vehicle, for monitoring and description of this space.
Yes.
After that, next task is to organize flying networks. For example, using Wi-Fi technology to transfer information from people or sensor to crisis center. And in this case, we will use this 3D model of this space. That's could your methods be applied for first part of this task, for identifying for identification of 3D spaces?
The whole space? Yes. If we
part by part.
If we consider, yes, of course, we could do it. But that's basically it. It's a domain. This domain can be.
Yes, because it is really in the condition of our country task. After destroyed building, there can be people. We need to understand. Or for example, after crashes or after accident on the industrial object, we need to understand which space we have to continue help of people or to collect information.
I see.
It's a task of identification in 3D space.
Yes, it could be used for sure, but to be honest, this method needs some improvements after that. Needs what I have in mind as post-processing. So I wouldn't say that it would be efficient compared to other methods, because it's very heavy computationally. Like these shapes took 10 minutes. Okay, might be not much, but when I tried a lot of points for the better result, it took a lot of time. So I would say that yes, it would probably have potential to be used, but after some post-processing, meaning some improvements. As I said previously, the main idea for this is to start from this. And with this in mind, you can create a lot more things. Of course, the identification of space, but of course, how fast, how good, how stable the result is, at least as far as I know, might be wrong, it's after that. So yes, it's what I'm currently working on, hopefully.
So if we go to the 3D, the sensors here are on the top.
Yes. Okay. So here, this was just a numerical result using a well-known program that uses that gives electromagnetic simulations in order to take, let's say, the measurements. It's one of the reasons I chose the perfect conducting case, and we use the measurements, as you will see. Here is obvious. So we send waves on green, which is around, so it's not good. But it is used and it is described. I haven't done the math, so when I haven't done the math, I can't say for sure anything. So they say that the same can be applied for interface analog. Like consider that we have a surface above water where we place the sources, and we take measurements on the level of the sea. The red dots will be on the level of the sea, and the object will be inside. So yes, if your question is if we take around the measurements, yes, but that was for my convenience to see how it behaves. Yes, but it transfers. At least that's what they say. I haven't tried it, but I'm pretty sure it will transfer to an interface case, and it will be a bit more realistic.
And also reflection. Depth could be explored those as well, or not. So the source of the top, they hit the object, but they also hit the bottom.
Reflections.
They reflect, and then we can
But we don't have any.
And also, if you go to the S1,
What? It's not that we don't have. We forbid the case of reflections.
I mean, if we have, could we use them as sources?
Probably wouldn't matter, because what we study is what the disturbance gave. So I don't know how would this affect the result. But in the end, what we study is what a disturbance that we got was. We don't have any implications on the boundary of box, but that's an interesting question. Okay.
That picture of the object surrounding.
Okay. Yes.
Yeah. So if we're talking about something inside in the water, it would be more realistic if we have water and then another medium at the bottom. Could we expand the analysis to have three now? So water, the object of interest, and then the bottom, which is sand or sand, whatever, rock. Could it?
I could say yes, but if I don't do the math, I can't answer. So we just add another layer.
So the bottom half or the bottom of the object has a different medium.
Yes, exactly.
The end will be on top. Then
Exactly. The interface analog. Yes, I would say yes, but I'm not sure to add another medium. I have no clue. I have no clue.
also you mentioned question.
Yes, because we like to we used our previous results. Our previous results were about chiral media. for electromagnetic waves, but that's not a limiting factor.
So if we had, because the picture that you showed, they might be hard. So if we did that with ultrasound, would it be possible to analyze?
In acoustics, yes.
Yeah. Okay.
Yes, it's exactly the same. The method as it is, the RGF method, is studied for all waves. Electromagnetic, elastic, acoustic, as far as I know.
The resolution will depend on the wavelength that you use. So with the electromagnetic, you get better resolution.
Okay, we work in the optical spectrum. We work in the optical spectrum. In the visible spectrum. Visible spectrum, sorry. With
Probably you need to check what the effect is in the resolution. With the optical spectrum, what resolution do you get? The shape of the body.
What do you see?
I can't see anywhere with my eyes.
Okay, it's there is no an already existing code. So I'm currently, this is a code I built, I wrote double precision, yes. And nah, you mean that much of details?
Yes.
But it wouldn't be realistic. It wouldn't be. I wouldn't do him a favor because this was for very few measurements. So that's why it also looks like candy. So it wouldn't be if I had the. Doesn't matter. It was just for example. But what I want to say is that if I had a supercomputer, let's say, then that would be okay. but I mean a good computer, like some results presented in some other works, not for this specific hybrid, but for a similar one, they had way better results. So, but they had some access to some really good computers and allowed them for better results.
Same question.
You want to be
one more. Just see. I remember the situation when I did opponent on one of the PhD students, and after commission questions, 1, 2, more, 2, bad, PhD students answer good. It was not PhD student, it was nice woman. And after stopping a question, let's ask you, why question finished? Please, Okay, thank you very much for your presentation, and we wish you success. Okay.
No, just yes. Sorry, we forgot to ask for online question. Is anyone online wanting to ask something? Okay, sorry for neglecting you this time. So this is the end of our session and today's sessions. Thank you for attending, and we'll meet again tomorrow.
Thank you.
Yes.